that life emerged. With 8 planets orbiting the Sun, it was the third Earth where life first appeared. Today, people are increasingly recognizing that the emergence of life is not simply the story of a single planet, but rather the product of a broader cosmic environment. A life-bearing world often depends on the support and protection of other celestial bodies. In this sense, it is more accurate to say that life was not only born on Earth, but within the solar system itself. Our solar system is remarkably structured, almost to a textbook degree of perfection, and this order may have played a crucial role in enabling life to arise. The 8 planets are divided into 2 clear groups, 4 large gas giants and 4 smaller rocky planets. Mercury, Venus, Earth, and Mars form the rocky inner worlds, while Jupiter, Saturn, Uranus, and Neptune form the gas giants that lie further out. Their arrangement is precise, with no size overlaps or orbital crossovers. The inner planets are spaced at almost regular intervals, roughly 50 million kilometers apart, and the outer giants too follow a consistent pattern. Every planetary orbit is smooth and orderly. This tight, harmonious alignment of planets forms a balanced, stable system. Whether such harmony is merely beneficial or absolutely essential to the birth of life remains uncertain. But what is clear is that the conditions for life on Earth were fragile and could have been easily disrupted by unfavorable cosmic factors. The very structure of the solar system may have offered Earth the protective environment it needed to nurture life into existence. These potential threats to life were, in fact, minimized to the greatest extent by our planetary system. Life emerged here, born from chaotic clouds of dust and gas. One could say that the planets of the solar system, orbiting in proximity, bore witness to the entire epic process of life's evolution, or perhaps even participated in it indirectly. These neighbors, who have accompanied Earth for the past 4.5 billion years, remain with us still, even though Earth itself has undergone dramatic transformation. What are they like now? Let's begin with Earth's closest planetary neighbor, Venus. Venus is incredibly bright, far more luminous than any star in the night sky. What makes it so distinct is that it always appears very low on the horizon, never high overhead. When it rises in the east, it does so just before the sun. When it appears in the west, it does so just after sunset. Because of this, Venus leaves a powerful impression. It seems to rule over the transition between night and day, standing as a symbol of both darkness and light. But why does Venus only appear near the horizon, and why is it so bright? The reason lies in its proximity to the Sun. Venus is the second planet from the Sun, orbiting about 50 million kilometers closer to it than Earth does. From Earth's perspective, Venus always appears close to the Sun in the sky, almost chasing it. When the Sun is up, Venus becomes invisible in the glare of daylight. It's only visible when the Sun is just below the horizon, during the early morning or late evening. Hence its nicknames, the morning star and the evening star. Venus is also incredibly bright because not only is it so close to the Sun and bathed in intense sunlight, but it is also the nearest celestial body to Earth after the Moon. Its reflective atmosphere amplifies its brilliance, making it one of the most striking objects in the sky when it appears. Interestingly, Venus is seen differently in various cultures. In Western mythology, particularly in Roman tradition, Venus was personified as Venus, the goddess of love and beauty. In the West, people believe that the brightest star in the sky must naturally represent the most beautiful, and so Venus became the embodiment of beauty and love. Venus, the Roman goddess. But in China, this luminous object in the sky was not seen as a symbol of beauty. Instead, it held deep spiritual and philosophical meaning. Venus was revered in Taoism as Tai Bai Jin Xing, the great white metal star, an important celestial figure. Taoism, represented by the ancient philosophers Laozi and Zhuangzi, emphasized harmony between yin and yang, coexistence, effortless action, and the pursuit of freedom within nature. It advocated a life of balance and transcendence. One could say that Taoist philosophy injected some of the most imaginative and romantic elements into the entire history of Chinese thought. China's most famous romantic poet Li Bai actually received his name from Venus. Legend has it that Li Bai's mother dreamt of Tai Bai Jin Xing before he was born, and thus named him Li Tai Bai. Steeped in Taoist ideals, Li Bai would go on to write countless celebrated poems that infused the mysterious spiritual legacy of Taoism into popular culture. His poetry radiated an unrestrained, free-spirited essence that left a lasting impression on Chinese spiritual and literary history. Venus, as a planet, is also strikingly similar to Earth. Its radius is 6,052 kilometers, only about 300 kilometers smaller than Earth's. Its volume is 88% that of Earth, and its mass is about 4/5 of Earth's. This resemblance led scientists to hope that Venus might also harbor life. After all, in theory, its conditions once seemed suitable for life to evolve. However, studying Venus has proven incredibly difficult. Despite being Earth's nearest planetary neighbor, its true face remained obscured for a long time. Unlike Earth's clear skies, where we can easily observe the surface from space, interrupted only by clouds of water vapor, Venus is completely shrouded in a thick blanket of clouds. From orbit, its surface is invisible. Before humans had the technology to pierce through Venus's dense cloud cover, some even speculated that it might be home to an advanced alien civilization. That mystery persisted until spacecraft finally reached Venus and deployed sophisticated instruments to peer through the haze. For the past 50 years, humans have launched around 40 missions to Venus, equipped with advanced instruments specifically designed to penetrate its clouds and analyze its surface. But the results were shocking. Not only did Venus show no signs of life, but it also seemed to manifest every worst-case scenario scientists could imagine for a planet. The surface of Venus is geologically similar to Earth, with mountains, plains, and canyons. But it lacks one crucial ingredient for life: water. Not a single drop has been found. Even more alarming, the surface temperature of Venus is nearly 500 degrees Celsius, hot enough to melt lead. We know that many microwave ovens operate at temperatures similar to those found on Venus. At such extreme heat, even metals with low melting points would liquefy. Clearly, water cannot exist on Venus, nor can any life that depends on it. What makes Venus even more daunting is not just its astonishingly high surface temperature, but the depth of its hot atmosphere, which is thick enough to completely envelop even its tallest mountains. On Earth, temperature drops with elevation, typically about 0.6 degrees Celsius for every 100 meters gained in altitude. That's why mountaintops are noticeably colder. Take Mount Everest, the highest peak on Earth, standing at 8,844 meters above sea level. If the temperature at sea level is 25 degrees Celsius, then on Everest it could drop below 55 degrees Celsius, a difference of more than 80 degrees. But on Venus, this rule does not apply at all. Venus also has towering mountain ranges, and its tallest peak, Maxwell Montes, rises to about 11,000 meters, more than 2,000 meters higher than Mount Everest. Yet even at this altitude, the temperature only drops by about 6%. Measurements show that while the surface temperature at Venus's lowlands is about 470 degrees Celsius, the summit of Maxwell Montes still bakes at around 430 degrees Celsius. This makes it arguably the hottest highland in the entire solar system, a true flaming mountain. Interestingly, despite the minimal temperature drop at high altitudes, Venus has abundant cloud formations at these heights. On Earth, clouds typically form when temperatures fall below degrees Celsius, making them a product of low temperatures. But on Venus, the clouds are not formed from water vapor. They are composed of hot sulfuric acid. In other words, even at altitudes of 10,000 meters, the clouds on Venus are blazing hot, forming a surreal phenomenon unique in the universe. These dense, near-boiling clouds of sulfuric acid sweep across the mountaintops like scalding fog. Ordinary rocks would likely be eaten away into Swiss cheese by this constant onslaught. The mountains of Venus must be composed of incredibly resilient materials, enduring endless washes of acid and heat, perhaps the most durable natural building materials in the solar system. Given this oppressive heat at all elevations, one might wonder whether Venus could be cooler on its dark side, away from direct sunlight. But Venus is nothing like Earth in its rotation. While Earth completes one rotation every 24 hours, Venus takes 243 Earth days to rotate once on its axis. Though it doesn't have a permanently dark hemisphere, it does have regions that remain in darkness for extraordinarily long periods. On Earth, if a region were deprived of sunlight for close to a year, its temperatures would plunge. For instance, Earth's polar regions receive sunlight at very low angles, yet that alone causes the average temperature at the poles to drop by nearly 100 degrees compared to the global average. The Arctic, for example, sees average temperatures of around minus 60 degrees Celsius. At Earth's South Pole, the average temperature can drop below minus 80 degrees Celsius. So, one might expect that the side of Venus that goes without sunlight for over 200 Earth days would be even colder than Earth's poles, completely deprived of solar warmth. Could this lead to a cold cycle on Venus? Surprisingly, data from space missions has proven otherwise. The entire planet of Venus maintains an incredibly consistent temperature. The sunlit side reaches a scorching 470 degrees Celsius, while the side facing away from the sun still simmers at over 430 degrees. In other words, even the side of Venus that hasn't seen sunlight in over 200 days remains nearly just as hot. On Venus, the absence of sunlight does not mean cool nights. Heat continues to radiate through the thick atmosphere. In effect, the sun has been reduced to little more than a light bulb for Venus. It distinguishes day from night, but barely influences the planet's temperature. In this sense, a thermometer becomes a deeply ironic instrument on Venus, because no matter where you place it, the reading is almost always the same. The entire planet functions like a massive thermal container, an insulated system that almost completely shields its surface from external changes. Venus has become a colossal heat retention chamber, storing heat far more efficiently than it receives from outside sources. This extreme condition is the result of 4.5 billion years of planetary evolution. Some argue that even if the sun were to disappear today, Earth would immediately plunge into an ice age. Venus, on the other hand, could remain almost unchanged for a very long time. Why is Venus so unbearably hot? A common assumption is that Venus is simply too close to the sun, about 50 million kilometers closer than Earth, and that it receives far more solar radiation, turning it into a blazing furnace. However, this explanation doesn't hold up under scientific scrutiny. Atmospheric analysis reveals that the surface of Venus actually receives less sunlight than Earth does. The reason lies in its atmosphere. Venus is enveloped by dense clouds of sulfuric acid, which form a thick orange-yellow layer stretching 20 to 30 kilometers deep. These clouds are so opaque and widespread that they block nearly 80% of the sun's light from reaching the surface. By contrast, Earth's only effective sunlight barrier is water vapor. While water-based clouds do reflect sunlight, they are incredibly thin and sparse compared to Venus's acidic cloud cover, only a fraction of its density. Thus, despite being closer to the sun, Venus actually receives less solar energy at the surface than Earth does. This leads to the critical question: if Venus receives less sunlight than Earth, where does its terrifying heat come from? The reason for Venus's extreme heat today isn't just the thick sulfuric acid clouds. It lies deeper, in an even more massive blanket of carbon dioxide that surrounds the planet. In fact, carbon dioxide makes up 96% of Venus's atmosphere, and the total amount of CO2 is hundreds of thousands of times greater than what we have on Earth. Carbon dioxide is an unusually stingy gas when it comes to heat. It lets heat in but doesn't let it out. Specifically, it allows shortwave solar radiation to enter the atmosphere. But once that energy is absorbed by the surface and re-emitted as long-wave infrared heat, CO2 traps it. This is the classic greenhouse effect. And on Venus, with such massive amounts of CO2, that effect has been pushed to the absolute extreme. So why does Venus, so similar to Earth in size and composition, have so much carbon dioxide, while Earth doesn't? Scientists believe the reason lies in Venus's inability to recycle its carbon. Any planet with active geology releases gases like CO2, but if these gases aren't somehow removed or stored, they will accumulate over time. Earth, too, had tremendous amounts of CO2 in its early atmosphere, tens or even hundreds of thousands of times more than today. If that CO2 had remained in the air, Earth would likely be just as hot as Venus. Fortunately, Earth has something Venus lacks: water. Water is the only effective medium for absorbing and removing carbon dioxide. When CO2 dissolves in water, it forms carbonic acid, which reacts with minerals to form calcium carbonate, better known as limestone. Over billions of years, Earth has locked away vast quantities of carbon dioxide in the form of limestone. In a poetic sense, it is the accumulated bones of life, alongside the magnificent karst formations that have helped shape Earth's blue skies and white clouds, our planet's natural identity. By contrast, Venus has no water. It cannot recycle its industrial exhaust, its carbon dioxide. As a result, CO2 has built up relentlessly, turning the planet into the hellish environment we see today. In a way, Venus is Earth's duplicate, a planetary sibling formed under similar conditions. But as we know, copies do not always share the same fate. In the cosmos, planets vary dramatically in size and character. In our own solar system, this diversity is clear. Planet masses differ by hundreds of times. Mercury's mass is only 5% of Earth's, while Mars is just 1/10. Uranus is 14 times Earth's size, Saturn is 95 times larger, and Jupiter dwarfs them all, 318 times the mass of Earth. And yet, amid this vast range of planetary scales, there is Venus, so remarkably similar to Earth in size and so close in orbit that its presence feels like an extraordinary cosmic coincidence. This may very well reflect a universal law that humanity has long overlooked. Next to a planet where life emerges, there might need to be another planet that closely resembles it. Earth gave rise to life, and right beside it, the universe placed Venus, a planet strikingly similar in size and composition. This arrangement seems to suggest that the birth of life requires not only macro-level conditions but also countless subtle details. And if even one of these microscopic variables deviates, the entire process may fail. Earth, then, could be the outcome of the universe choosing one of two options: Venus or Earth, and ensuring that Earth had just enough of the right conditions, perhaps only slightly more favorable than Venus, to make the miracle of life possible. It leads to a compelling thought. If the solar system had only Earth and no Venus, would life still have formed on Earth? This remains an open and unsettling question. Without a doubt, Earth is now a planet teeming with life. Its size appears to be a golden size prepared by the universe for life, large enough to maintain a stable atmosphere and plate tectonics, yet small enough to regulate internal heat and sustain liquid water. This ideal size allows physical and chemical forces to operate in perfect harmony, supporting life as we know it. And yet, Venus, which shares this same golden size, raises a giant question mark. What exactly went wrong for Venus? Why did it fail while Earth succeeded? Today, many experts believe that the key difference lies in the presence of a moon. Earth has a satellite, the moon, while Venus does not. And this difference, as subtle as it may seem, might be deeply tied to their orbital positions and early solar system dynamics. The moon has a truly extraordinary origin. Scientific evidence now confirms that its composition is nearly identical to Earth's, with isotope ratios so similar that the two must be of common lineage. Moreover, lunar dynamics indicate that the moon is slowly drifting away from Earth, implying that it was once much closer. Modern science has gone a step further. The moon was likely once part of Earth itself, torn away during a catastrophic impact in the distant past. This event not only reshaped our planet, but may have provided the stability and conditions necessary for life to arise. The moon was born from a cataclysmic impact. Around 4.5 billion years ago, a planet roughly the size of Mars collided violently with the early Earth. As this planet shattered upon impact, a portion of Earth's material was ejected into space. These fragments gradually coalesced into a new celestial body, the moon. But more importantly, this collision endowed Earth with a crucial angular momentum, a sideways rotational energy that accelerated Earth's spin. This rapid rotation kick-started Earth's internal dynamo, the system that powers its magnetic field. Earth's inner structure functions much like a massive generator. Its interior is filled with superheated, electrically charged plasma. When this plasma rotates, it generates electric currents, and with them, a magnetic field. This magnetic field would become the guardian of life, the shield that made water and thus life possible. Why is this magnetic field so vital? Because it blocks the solar wind, the stream of charged particles constantly blowing from the sun. Without this protection, Earth's water would have been stripped away. The sun, for all its brilliance, is in fact a massive and unruly nuclear furnace. It has no filters, no safety valves. At its core, nuclear fusion reactions constantly occur, slamming atomic nuclei together and unleashing immense energy. This energy radiates outward, heating the sun's surface and flooding the solar system with light and heat. Because it blocks the solar wind, the stream of charged particles constantly blowing from the sun. Without this protection, Earth's water would have been stripped away. The sun, for all its brilliance, is in fact a massive and unruly nuclear furnace. It has no filters, no safety valves. At its core, nuclear fusion reactions constantly occur, slamming atomic nuclei together and unleashing immense energy. This energy radiates outward, heating the sun's surface and flooding the solar system with light and heat. But this nuclear furnace also produces waste, and unlike a clean, well-contained system, the sun violently expels this waste into space in the form of charged particles, the solar wind. These particles are far from gentle. Unlike the soft light of the sun, they bombard everything in their path, smashing apart vulnerable molecules, including water molecules. It's this chaotic, unrelenting barrage of solar wind that makes the emergence of life in the universe so extraordinarily difficult. Without a protective magnetic field to shield its atmosphere and water, a planet, even one as well-positioned as Earth, would quickly become barren. In the vast universe, the most essential substance directly supporting life is water. A water molecule is remarkably simple, composed of just 2 hydrogen atoms and 1 oxygen atom. The universe did not design it to be particularly robust. In fact, water molecules are quite fragile. When exposed to the charged particles from the sun, they can be easily broken apart, their molecular bonds shattered. Without protection, water molecules cannot survive near the sun. And without water, life cannot exist. This is likely one of the key reasons why life is so rare in the universe. To sustain life, a planet must be close enough to a star to receive energy, but it must also have a shield to protect its water resources from being destroyed by the solar wind. This shield is the planet's electromagnetic field. It lets in light and heat, but keeps out the damaging charged particles. In this sense, Earth's electromagnetic field is nothing short of a guardian spirit, the protector of water, and by extension, of life itself. Interestingly, Venus also once had water. On a planet with conditions so similar to Earth's, it's almost certain that water existed in the beginning. In fact, scientists have detected large amounts of hydrogen isotopes in Venus's atmosphere. These isotopes are the remnants of water molecules split apart by solar radiation. Their abundance suggests that Venus once held vast quantities of water. But in the early solar system, planets didn't just rely on their initial water reserves. There was a vast cosmic delivery service supplying them with additional water, comets. Comets are gigantic frozen snowballs originating from the Kuiper Belt, the icy reservoir at the edge of the solar system. In the early solar system, comets were far more numerous than they are today, constantly transporting frozen water to various planets. The universe does not lack water, it has plenty of ice reserves. What the universe does lack are swimming pools, places where ice can melt into liquid water. This is the real challenge, not creating water, but sustaining it in a liquid state on a planet's surface. So far, only Earth has succeeded. When we gaze at the long tails of comets streaking across the sky, we are witnessing more than a beautiful celestial event. We are catching a glimpse of life's potential. These icy messengers carry the ingredients of life, but most of them fade into loneliness, unable to find a suitable harbor where they can settle and release their treasures. Thus, water and the building blocks of life roam the universe in abundance. But all too often, they are wasted in the silence of space, never finding a home. In the universe, this age-old delivery of water by comet fleets has continued unchanged for eons. Like a routine mission, these icy couriers travel door to door, supplying water to every planet, including Venus. But Venus failed to protect its water resources. Unlike Earth, it did not experience a major collision, and thus did not gain rapid rotation or generate a magnetic field. As a result, its water was quickly destroyed and swept away by the solar wind. In the end, Venus became a completely arid planet. Today, not even a trace of water vapor remains on Venus. Its skies are filled with clouds tens of kilometers thick, but it never rains, because these are scalding clouds of sulfuric acid. Without water, carbon dioxide could not be recycled. Over billions of years, the CO2 concentration on Venus has only increased, now reaching levels hundreds of thousands of times greater than on Earth. This led to an extreme greenhouse effect. By contrast, although Earth's early surface was also blisteringly hot, perhaps devoid of any liquid water, with all moisture existing as vapor, Earth's magnetic field protected this vapor. It remained in the atmosphere, never stripped away by solar wind. As the planet gradually cooled, this vapor condensed and fell to the surface, forming oceans. That's when Earth's carbon dioxide recycling process began. Today, Earth's CO2 levels are only 1/10,000th of Venus's, a direct result of water's ability to recycle atmospheric gases. The CO2 that once plagued Earth's atmosphere is now locked away in solid form as calcium carbonate, better known as limestone. Today, limestone is a source of natural beauty, but billions of years ago, the gases that formed these rocks tormented Earth with intense heat. It was water that solidified them and anchored them to the crust, completing the construction of a planet fit for life. One could say that Venus and Earth diverged solely because of one dynamic difference. Earth suffered a collision that gave rise to a magnetic field, while Venus did not. This led to entirely different evolutionary paths. This dynamic advantage, the result of a collision, was likely determined by subtle differences in orbital position. Earth, being slightly farther from the Sun, may have been more likely to be hit. Venus, being closer to the Sun, may have had potential impacts deflected or disrupted by the Sun's stronger gravitational interference. So in this sense, the different fates of Earth and Venus may ultimately be traced to their distance from the Sun, a subtle but crucial factor. It suggests that even with all necessary conditions met, the birth of a life-bearing planet still requires a measure of luck. Perhaps if the collision had occurred on Venus instead of Earth, Venus would now be the cradle of life, and Earth a lifeless furnace. But since collisions are inherently unpredictable, was it really necessary to have two nearly identical planets just to try one with a lucky hit? At least in our solar system, the answer seems to be yes. Today, Venus seems to serve as a failed counterpart to Earth, an alternate outcome in the evolutionary story of terrestrial planets. And this stand-in offers us a rare opportunity, a glimpse into what Earth might look like after 4.5 billion years if it lacked both a magnetic field and water. In other words, Venus allows us to imagine a version of Earth stripped of its protective features and life-sustaining systems. On Earth, the most significant geological force shaping the planet's surface is plate tectonics. This powerful force originates from internal heat within the mantle, which drives the constant renewal and recycling of Earth's crust, breaking apart old crust and forming new layers. As a result, most of Earth's surface is relatively geologically young. Venus, much like Earth, has a similar amount of internal heat, which also drives surface renewal. However, the way that renewal takes place on Venus is entirely different. Venus relies on volcanoes to reshape its surface. Studies suggest that Venus may host hundreds of thousands of volcanoes, compared to only a few thousand on Earth, and they are distributed all across the planet. Scientists believe that this extreme volcanic activity on Venus is due to its lack of plate tectonics. Without moving tectonic plates to gradually release internal energy, Venus is forced to vent its heat through an overwhelming number of volcanic eruptions. Why doesn't Venus have plate tectonics? One theory is that Venus never experienced the kind of massive impact that Earth did. Earth's violent collision with a Mars-sized body, known as Theia, not only gave it its rapid rotation, but also ejected a significant portion of its outer crust, eventually forming the Moon. That impact thinned Earth's crust, making it more dynamic and easier to shift. This theory is supported by density measurements. The Moon has about half the density of Earth, matching the composition of Earth's outermost, lightest layer. It's believed that the Moon formed from Earth's ejected crustal material. However, many geologists point to the presence of water as an even more critical factor in enabling plate tectonics on Earth. Water plays multiple roles. It softens the rigid crust, making it more flexible and easier to fracture. Through tidal forces generated by the Moon, water applies rhythmic stress to the lithosphere, encouraging it to crack and shift. These forces allow Earth's crust to move, forming the dynamic, living planet we know. By contrast, Venus has a much thicker and more rigid crust, which is resistant to deformation. Without water and without a rotating magnetic shield, Venus lacks the means to generate plate tectonics. As a result, Venus has become a planet ruled by volcanoes. Its internal heat builds up over time and can only escape in violent bursts, turning the surface into a fiery, molten battlefield, an expression of trapped planetary energy with no path to release. Igneous rock and Venus's fiery surface, volcanic materials ejected by eruptions, have covered approximately 85% of Venus's surface, creating a planet overwhelmingly shaped by fire. Rivers of molten lava have streamed across its lowlands, forming channels thousands of kilometers long, the longest of which stretches over 7,000 kilometers, longer than the Yangtze River on Earth. This extraordinary lava flow distance is likely due to Venus's extremely high surface temperatures, which significantly delay the solidification of lava. As a result, the molten rock can travel great distances before cooling and hardening. Venus thus reveals to us a haunting possibility. On a planet similar to Earth, in the absence of cool, flowing rivers of water, there may instead exist rivers made entirely of burning lava. Earth's surface, by contrast, is geologically young because of its dynamic tectonic plates. These plates constantly move across the crust, causing land masses to shift, new mountains to rise, and ancient seafloors to vanish. Earth's terrain is always undergoing massive reconstruction, like a constantly evolving, reassembled puzzle. Surprisingly, Venus's surface is also considered geologically young, nearly as youthful as Earth's, but not for the same reasons. Rather than through destruction and tectonic renewal, Venus refreshes its surface through widespread volcanic activity. But instead of replacing its crust, Venus merely repaints it. Imagine the difference this way. Earth tears down and rebuilds its crust like demolishing and reconstructing buildings. Venus, on the other hand, continuously lays new coats of volcanic paint, thick layers of lava and ash over billions of years. While this process refreshes the appearance, it doesn't truly alter the ancient underlying structure. As a result, Venus preserves traces of its early landscape, offering a unique window into the kind of environment Earth may have once had. In the early solar system, violent asteroid and meteor impacts were a common occurrence. Rocky planets, including Earth, bore the scars of countless collisions, visible in the form of impact craters. However, today we see very few impact craters on Earth. That's because Earth's tectonic activity and constant weathering through wind, rain, and erosion have erased most of those ancient marks. On Venus, although volcanic eruptions continually blanket the surface, they don't destroy old geological formations with the same intensity as plate tectonics. As such, much of Venus's terrain still reflects conditions from billions of years ago, making it an invaluable reference for understanding what Earth's surface might once have looked like. Yet, despite being so old, Venus's surface is surprisingly smooth compared to other rocky planets like Mercury or the Moon, which are covered with craters. So why does Venus have so few impact craters? Experts believe the answer lies in Venus's dense atmosphere. When meteors plunge toward the planet, they encounter such thick atmospheric resistance that most are incinerated before reaching the ground. Only about 1% of larger meteors manage to survive the descent and impact the surface. Interestingly, scientists think early Earth may have had an atmosphere much like Venus's, rich in carbon dioxide. At that time, this dense atmosphere may have played a crucial role in protecting early life from frequent, catastrophic impacts. After all, during the fragile stages when life was just beginning to emerge, even a moderate-sized meteor strike could have spelled extinction. In that sense, a carbon dioxide-laden atmosphere may have been a temporary shield, buying life enough time to gain a foothold. The intense greenhouse effect may slowly strangle a planet, but in the early days, it may have actually saved life from destruction. It was precisely because of Earth's early thick carbon dioxide atmosphere that life was able to survive countless extinction-level collisions. In that sense, we should be grateful for CO2 and its protective role in Earth's infancy. Of course, as the solar system gradually stabilized, asteroid and meteor impacts became increasingly rare. The planets eventually passed through their dangerous adolescent phase, and that thick protective layer of CO2 was no longer needed. As the probability of impacts decreased, Earth's carbon dioxide levels also declined accordingly. Once the cosmic air raid alarms were silenced, CO2 settled down to a trace presence in our atmosphere. At the heart of it all, it was the ancient cosmic collision, Earth's acquired rotation, and the birth of the magnetic field that changed the planet's fate, allowing us to live so close to the sun and still praise it wholeheartedly, without fearing its more violent side. That's why we must be deeply thankful for the great impact over 4 billion years ago. We should gaze at the moon, the byproduct of that monumental collision, with a sense of awe and gratitude. It is not only a celestial companion, but also a participant in Earth's water preservation and carbon dioxide recycling systems. Though Venus often receives harsh judgment for its harsh conditions, when we look across the cosmos, we realize that Venus is actually an extraordinarily rare and precious world. Humanity has always held hopeful expectations about the universe, constantly searching for planets similar to Earth. Indeed, we've found some planetary systems that resemble our own. In several of them, we've even found multiple planets orbiting stars much like our Sun. But do any of these planets come close to resembling Earth? The first planetary system similar to ours that scientists discovered was 51 Pegasi, located 49 light-years away. Its central star is similar to the Sun. In 1995, astronomers found a planet orbiting it, a gas giant about 150 times the mass of Earth, comparable in size to Saturn. The largest exoplanetary system discovered so far is 55 Cancri, which hosts 5 planets. However, these are all massive gas giants, lacking any planet remotely similar to Earth or Venus. Even the smallest among them is 80 times more massive than Earth or Venus. Finally, in April 2007, scientists discovered a planet that came somewhat close to Earth and Venus in size, Gliese 581e, located only 20.4 light-years from Earth. It remains the smallest and most Earth-like exoplanet found to date. However, even Gliese 581e is 50% larger than Earth and twice as massive. Through extensive research beyond our solar system, we've come to a striking realization. Among all the exoplanets we've found, finding one with the same size and composition as Venus, so similar to Earth, is incredibly rare. And yet, even Venus, with just one crucial misstep, became so utterly hostile to life. So the probability of finding planets in the universe that can harbor life is very small. Still, humanity will never stop searching, because we already know that the cosmic material system is capable of creating life. And Venus, our closest neighbor, still holds more hope for life than any other planet we know. It remains like an unopened life factory, storing untapped potential. Billions of years ago, Venus handed the luck of life to Earth, and now perhaps it's time for Earth's life forms, its beneficiaries, to return the favor. On September 14, 1978, the Soviet Union launched the Venera 12 probe. During its descent to Venus, it recorded frequent lightning flashes and thunderous rumbling in the planet's thick atmosphere. In just the short span, from 11 kilometers down to 5 kilometers above the surface, it detected over 1,000 lightning discharges. Each bolt of lightning on Venus carries over 50 million volts, an astonishing amount of energy, enough to alter the planet's atmospheric chemistry and molecular environment. Perhaps it's this cosmic electrical power that can fuse inorganic substances into organic compounds. As long as lightning still flashes, Venus still holds the hope of life. Of course, this hope can only become reality if we first change Venus's hellish conditions. Now we know, the divergent fates of Earth and Venus can be traced back to a single ancient impact, the collision that formed the Moon. So what if we made a bold proposal? What if humanity deliberately induced a massive impact on Venus, one powerful enough to tilt its rotation and give it a rapid spin? If that happened, the plasma deep inside Venus would start to rotate, generating a magnetic field. Venus, the dormant factory of life, could finally be activated. With a magnetic shield in place, solar wind would be deflected, and water could survive on Venus. While the solar system may no longer deliver water via cometary transport, humans could step in to provide it. Maybe someday, using our own technological power, we could terraform Venus into a habitable world. At that point, the solar system would evolve into a multi-planetary life network, a true system of worlds united by life. If that day ever comes, it would be the greatest expression of gratitude humanity could offer to Venus, a planet we so often regarded with criticism and pity. It would also mark the most profound expansion of human stewardship over cosmic resources. As our exploration of the solar system deepens, scientists are discovering that its bodies are far more numerous and diverse than once imagined. Especially among the giant planets, we now know that each has an abundance of moons, making them vast reservoirs of satellite resources within the solar system. Among all the planets in the solar system, Jupiter has the most moons. As of now, scientists have discovered 61 moons orbiting it. The first moons ever discovered beyond Earth's own moon were Jupiter's 4 largest satellites, known as the Galilean moons: Io, Europa, Ganymede, and Callisto. It was these very 4 moons that enabled Galileo Galilei to support Copernicus's heliocentric theory. Their clearly visible orbits around Jupiter, rather than around Earth, directly contradicted the geocentric model, which claimed that all celestial bodies revolve around Earth. This discovery not only undermined medieval European religious doctrine rooted in geocentrism, but also ushered in a new era of scientific enlightenment. However, it wasn't until nearly 400 years later, in 1979, that human spacecraft, after traveling 800 million kilometers, finally approached these influential celestial bodies for direct study. The first of the Galilean moons, Io, measures 3,642 kilometers in diameter, slightly larger than Earth's moon. What's most remarkable about Io is its intensely active volcanic activity, the most extreme in the entire solar system. In March 1979, as NASA's Voyager 1 flew past Jupiter, it captured images showing 9 volcanoes actively erupting on Io. This marked the first time humans had ever witnessed volcanic eruptions on a celestial body other than Earth. Just 4 months later, Voyager 2 arrived and discovered something even more astonishing. The volcanoes that had been active were now dormant, while others had begun erupting. This rapid shift indicated extraordinary and continuous geological activity. Ejecta from Io's volcanoes can be blasted up to 300 kilometers into space, a staggering feat for a moon roughly the size of our own. So where does all this volcanic energy come from? Scientists believe that Io's titanic internal heat is generated by tidal forces created through gravitational interactions, not only with Jupiter, but also with its fellow moons Europa, Ganymede, and Callisto. These moons, engaged in a gravitational tug-of-war, cause Io to flex and distort by up to 100 meters. This constant flexing generates tremendous internal friction and heat, fueling the moon's volcanic fury. Io is a true mountain of fire. Its entire surface is blanketed in volcanic deposits. With the planet's inner materials constantly being brought to the surface, Io is essentially disemboweling itself, exposing its internal structure. Visually, Io looks like a gigantic otherworldly abstract painting, a chaotic masterpiece of yellow, red, and orange. Scientists believe that analyzing Io's surface directly reveals the composition of its interior, making it a natural laboratory for understanding planetary geology. But next door to fiery Io is Europa, a stark contrast. Europa is a sealed world of ice, and its diameter is 3,138 kilometers, slightly smaller than Io's. Slightly smaller than the Moon, Europa is a moon tightly sealed beneath a thick, icy shell. While we often say that water is scarce in the universe, Europa is a gigantic cosmic reservoir. If all its ice were to melt, it would hold several times more water than Earth. Europa is one of the brightest moons in the solar system, not only because it's encased in ice, but because this ice shell is incredibly smooth, giving it a striking shine. But upon closer inspection, Europa's surface is crisscrossed with dark lines, jagged features, and scattered blotches, large or small, round or oval, that scar its otherwise smooth exterior. These markings may be caused by volcanic or hydrothermal eruptions, suggesting internal activity. The Galileo spacecraft has returned the latest images indicating that beneath Europa's icy crust lies a vast ocean of liquid water. The surface ice is estimated to be only 1 to 2 kilometers thick in some areas. At Europa's surface temperature of -106 degrees 250 Fahrenheit, water should not exist in liquid form. So why is there liquid water? One explanation is that Jupiter's immense gravity exerts tidal forces on Europa, causing its internal materials to expand and contract, generating heat from friction that melts the ice into water. Another hypothesis suggests that Europa might have subsurface volcanic activity similar to its neighbor Io. These volcanoes could be generating heat from below, keeping the water in liquid form. Some even believe that water might occasionally erupt through cracks in the ice, creating the patchy surface textures and ridges seen from orbit. Yet another explanation lies in the sheer volume of water. Probes suggest Europa's ocean could be tens of kilometers deep, much deeper than Earth's oceans. Earth's average ocean depth is about 3,730 meters, but scientists believe Europa's subsurface ocean could reach more than 50 kilometers in depth. This extreme depth introduces a new physical effect we rarely encounter. Although temperatures might remain well below freezing, say -55 degrees 7 degrees, the immense pressure from the overlying ice could raise the melting point of water, preventing it from freezing despite the cold. If future probes confirm this, Europa would truly be a water world, not only containing more total water than Earth, but also maintaining a sealed, cold, and deep subsurface ocean that may harbor conditions suitable for life. Where there's water, there's potential for life. As a result, Europa has captured the scientific world's imagination. Some researchers have even speculated that the network of grooves and cracks on its surface might be linked to biological processes, though this remains highly speculative. Beneath Europa's icy shell, it's highly possible that some form of energy or even life already exists, a presence that may have penetrated or even influenced the moon's environment. Of course, the existence of life is still just a hypothesis, but the abundant presence of water on Europa gives humanity a renewed hope, as if long-parched souls finally found sweet rain. This possibility has expanded our understanding of water beyond Earth. It suggests that the moons of the solar system might provide alternative environments for life that planets alone do not offer. To date, Jupiter is known to have 61 moons, forming a vast and intricate family. This abundance aligns well with Jupiter's status as the largest planet in the solar system. Most of these moons are thought to have been captured by Jupiter's gravity, and because they come from different origins, they offer a wide range of physical forms and material compositions, making Jupiter's moons a massive resource library for planetary science. Saturn, the second largest planet, also boasts an extensive moon system, with each moon having its unique characteristics. Take Saturn's moon Phoebe, Saturn 9, for instance. It's about 200 kilometers in diameter, irregular in shape, and the only known retrograde moon of Saturn, meaning it orbits in the opposite direction compared to most other Saturnian moons. This opposite motion likely explains why Phoebe has suffered heavy impacts, leaving it covered in craters and scars, almost entirely battered. What's more interesting is that Phoebe's bombardment has affected its neighbor, Iapetus, Saturn 8. Over billions of years, the debris ejected from Phoebe during impacts has rained down on Iapetus. Even though the probability of these particles landing is low, after billions of years, even a 1 in 10,000 chance accumulates into a significant effect. As a result, Iapetus has developed a bizarre appearance, earning the nickname Yin-Yang Moon. Its diameter is about 1,460 kilometers, roughly one-third the size of Earth's moon, and with a low density of about 1.1, it's mostly composed of ice. It's believed that Iapetus may once have been a pristine white moon, but now only one side remains bright, while the other is pitch black, as though its dark-skinned neighbor smeared its face with soot. Then there's Titan, Saturn 6, the largest moon of Saturn and the second largest moon in the solar system. Titan is also considered the most likely place in the solar system to harbor life. Titan is the only moon with a dense atmosphere, composed of 98.44% nitrogen and rich in various hydrocarbons, organic molecules critical for life. This makes Titan unique among all satellites, the only one to have a true atmosphere. Until recently, humans had very limited understanding of Titan's surface. Due to its dense atmospheric clouds, visible light is almost completely blocked, making direct observation nearly impossible during the era of optical astronomy. Scientists long suspected that Titan's surface consisted mainly of solid or liquid ethane. But on August 1, 2008, scientists analyzing images from the Cassini spacecraft confirmed that Titan has lakes. Not only has this dense atmosphere prevented Earth-based observations, but the sunlight barely penetrates to Titan's surface, which is perpetually dim and murky. So when Cassini deployed the Huygens probe and it descended onto Titan's surface, the moment was nothing short of extraordinary. Although the Huygens probe successfully transmitted many images from the surface of Titan, the extremely weak lighting made it difficult to discern the actual conditions of Titan's terrain from the photos. To better understand the surface features, the Cassini spacecraft employed remote radar sensing when it approached Titan. The very first radar image revealed a surface with a mix of rugged and smooth areas, which seemed to have been shaped by volcanic activity, possibly volcanoes that erupt water and ammonia. In addition, some regions appeared to have striated landforms, likely shaped by wind erosion, and a number of filled-in impact craters, possibly containing liquid hydrocarbons. Whether these lakes truly contain liquid, or what substances they might hold, remains uncertain. Some areas returned radar signals that could correspond to solid or liquid surfaces, though alternative interpretations still exist. Titan appears remarkably smooth, with no terrain features higher than 50 meters. At least one large liquid hydrocarbon sea has been identified, dotted with numerous island-like features. As for whether life might exist on Titan, NASA reported two intriguing findings. First, hydrogen gas present in Titan's upper atmosphere mysteriously disappears near the surface. This led to speculation that something on the surface, possibly microbial life, might be consuming the hydrogen. Second, the Cassini probe found that a specific chemical compound was missing from Titan's surface. Scientists theorize that this compound may also have been metabolized by some form of life. If these observations do in fact indicate biological processes, it could mean that life in the universe may not be limited to water-based forms. Titan may harbor methane-based life, a completely alternative biochemistry. While Titan gives humanity hope of finding an atmosphere-bearing rocky world, Enceladus, Saturn's moon, also known as Saturn II, represents a different kind of world altogether. Enceladus is a tiny, dazzlingly bright satellite embedded in Saturn's icy rings, with a diameter of less than 500 kilometers. For a long time, it was considered a rather ordinary ice moon. In 1981, Voyager 2 captured a few photos of it, but those limited images puzzled planetary scientists for decades. Despite Saturn's moons being diverse and unpredictable, Enceladus stood out as especially unusual. Its ice-covered surface was strikingly bright, like fresh fallen snow, and large, smooth plains devoid of impact craters were found. This strongly suggested that the moon had experienced internal geologic activity, which resurfaced and erased the scars of past impacts. But Enceladus is too small to generate the amount of internal heat typically required for such activity. Clearly, something extraordinary had occurred, or the massive craters caused by past impacts wouldn't have just vanished. Voyager's fleeting visit ignited scientific curiosity, making Enceladus one of the primary targets for the Cassini-Saturn mission. In 2004, Cassini conducted an unprecedented close flyby and made a groundbreaking discovery. From Enceladus's south pole, massive plumes of water vapor were erupting into space like geysers. This water, a vital ingredient for life, was being ejected as high as 430 kilometers, so forcefully that it even struck Cassini as it flew past the moon at high speed. As the Cassini spacecraft flew past Enceladus, Saturn's icy moon, it observed a geyser eruption every 8 minutes. These geysers weren't merely expelling water, they were mixed with organic compounds essential for life, including methane, propane, ethylene, and carbon dioxide. These substances were ejected into the outer E-ring of Saturn, enriching the ring system with organic material. Cassini was equipped with a spectrometer, which it used to perform chemical analysis of these icy plumes. The instrument detected strong emissions of ethylene and propane, indicating that beneath Enceladus's surface, the temperatures might reach between 440 degrees Celsius and 980 degrees Celsius, far higher than one might expect beneath a small icy moon. In 2007, astronomers at the Lunar and Planetary Science Conference proposed that radioactive decay within Enceladus's core might be the source of its sustained internal heat. With the presence of a subsurface heat source, organic molecules, and liquid water, Enceladus meets the 3 key criteria for the potential development of life. Of course, it is still far too early to confirm the existence of life. Nevertheless, by 2008, before completing its mission, Cassini made one final flyby of Enceladus, providing crucial data. Scientists and space agencies continue to eagerly await the release of new findings from this dataset. Moving from Saturn to Uranus, Uranus possesses 29 known moons, each with distinctive geological features. Among them, Miranda's stands out as the smallest and closest major moon. Composed of approximately equal parts ice and rock, Miranda's surface is rugged and scarred with numerous impact craters, deep chasms, valleys, and cliffs. Its terrain looks like a patchwork quilt, suggesting that intense geological activity once shaped its surface. Scientists believe that Miranda has undergone multiple cycles of destruction and reassembly, each time exposing interior material and altering the moon's original surface. However, a more recent and widely accepted theory suggests that these features may have been caused by melting ice, where subsurface heat causes internal movement and surface deformations. Neptune's unique moon. Triton Neptune has around 13 known moons, making it the giant planet with the fewest satellites. Yet among these moons is one that is truly exceptional, Triton, Neptune's largest moon. Triton has a diameter of 2,700 kilometers, making it slightly larger than Pluto. It is geologically active, with a young surface and very few impact craters, indicating recent resurfacing. During its flyby, Voyager 2 observed numerous cryovolcanoes on Triton's surface. These cold volcanoes were seen erupting fountains of nitrogen, dust, or methane mixtures, some of which reached altitudes as high as 8,000 meters. Unlike the hot volcanoes of Io, Triton's cryovolcanism may not be caused by tidal forces but rather by seasonal solar heating. Curiously, the materials ejected from Triton's volcanoes tend to curve mid-flight, likely due to the influence of Triton's gravitational field or its thin atmosphere. It is suspected that Triton's orbit plays a critical role in this unique geophysical behavior. Triton's orbital path is tilted at an extraordinary 157 degrees relative to Neptune's rotational axis, a configuration completely unlike that of Neptune's other moons. In essence, Triton orbits almost vertically, passing over Neptune's north and south poles like a probe. This unique orbit means that one of Triton's poles faces directly toward the Sun every 82 years, as Neptune completes one orbit around the Sun. The result is extreme seasonal changes on Triton's surface. Interestingly, the cryovolcanoes on Triton appear to follow this seasonal cycle, erupting in alignment with these long-term solar exposures. Even more astonishing is the discovery that Triton possesses a magnetic field, a characteristic generally found only in much larger planets. Data from Voyager 2 confirmed that Triton has an enormous internal core, which accounts for 2/3 of the Moon's total mass. If this core is metallic, it likely generates Triton's magnetic field. This finding is significant because, like the presence of water, a magnetic field is considered one of the crucial conditions for supporting life. While it's not uncommon for celestial bodies to have water, it is extremely rare for a small body like Triton to possess a magnetic field. This suggests that even relatively small objects in the solar system can host substantial internal energy systems, which could have broader implications for planetary science and astrobiology. Within the solar system, moons form a vast and diverse group. They are small worlds with a wide variety of shapes, geological histories, and chemical compositions. Many of them exhibit astonishing and unexpected features, hinting at complex links to different stages of solar system evolution, whether from its early history or more recent events, whether in the inner solar system or the distant outskirts. In this sense, each moon can be seen as a unique cosmic structure, a distinct stage in the ongoing evolution of universal matter. As we continue to deepen our understanding of these satellites, we may uncover even more surprising discoveries, findings that will broaden humanity's view of the cosmos. Perhaps more inspiring is the fact that these satellites are not just scientific curiosities. They represent untapped resources within the solar system. If humanity continues to advance its technological capabilities and space development tools, it is entirely possible that our civilization will one day expand to these moons. When that happens, Earth's civilization will reach a new level of transcendence. Back in 1772, the German astronomer Johann Elert Bode published in his book Anleitung zur Kenntnis des gesternten Himmels a numerical pattern originally proposed by physicist Johann Daniel Titius. This pattern sought to predict the distances of planets from the Sun using a specific number sequence: 0, 3, 6, 12, 24, 48, and so on. Adding 4 to each number and dividing by 10 yields approximate planetary distances in astronomical units. This empirical rule would later become known as the Titius-Bode law, a curious and influential theory in the study of planetary orbits. According to calculations, the distances between the 4 planets closest to the Sun, Mercury, Venus, Earth, and Mars, showed an astonishing match with a mathematical rule. Specifically, if Earth's distance to the Sun is taken as 1 astronomical unit, AU, then Mercury lies at 0.4, Venus at 0.7 AU, and Mars at approximately 1.6 AU. This remarkable alignment raised a major question in the scientific community. Could the solar system truly be governed by a mathematical model? Following this logic, the 5th planet from the Sun should be located at 2.8 AU. However, at that time, no planet had been discovered at this position, casting doubt on the rule. The most distant planets known then were Jupiter and Saturn. Applying the same rule predicted that Jupiter should be at 5.2 AU and Saturn at 10 AU. In reality, Jupiter is 5.203 AU away from the Sun, and Saturn is 9.554 AU, a stunningly precise match. This led many astronomers to believe that a planet must exist at the 2.8 AU mark, but humanity simply hadn't found it yet. In 1781, British astronomer William Herschel accidentally discovered the solar system's 7th planet, Uranus. Its average distance from the Sun is 19.2 AU. Using the rule, 96 plus 4, 10, 19.6, again, the prediction closely matched reality. Confidence in the Titius-Bode law, as the rule came to be known, was now stronger than ever. Most astronomers agreed, a planet must exist at 2. AU, just waiting to be discovered. But more than a decade passed, and still, no planet appeared. On New Year's Eve of 1801, Italian astronomer Giuseppe Piazzi was carefully scanning the night sky. Suddenly, he spotted a very small celestial body located exactly where the Titius-Bode law predicted, at 2.8 U. However, soon after his discovery, Piazzi fell ill. By the time he recovered and resumed observation, the object had disappeared. Nevertheless, Piazzi was convinced that he had stumbled upon the long-sought planet and named it Ceres. The astronomical community was divided. Some believed Piazzi's discovery was valid, while others suspected it might have been a comet, reasoning, if it were truly a planet, why had it vanished so quickly? Months passed, yet the debate remained unresolved. However, this ongoing debate caught the attention of the German mathematician Carl Friedrich Gauss. Gauss believed that if astronomers couldn't locate Ceres through observation alone, perhaps mathematics could offer a solution. Through rigorous calculation and his exceptional mathematical talent, Gauss developed a new theory for computing planetary orbits. Using Piazzi's original observations, Gauss needed only 1 hour to determine the shape of Ceres' orbit and predicted the exact time and location where it would next appear in the sky. On the night of December 31, 1801, German amateur astronomer Heinrich Olbers pointed his telescope toward the region of the sky Gauss had predicted. And there it was. Ceres had reappeared, precisely as Gauss had calculated. Yet further observations soon revealed a puzzling detail. This supposed fifth planet was shockingly small. Ceres had a diameter of only about 1,120 kilometers, just 2/7 the size of Earth's moon, and its mass was merely 1/50th of the moon's. This revelation left astronomers confused. How could such a vast gap in space contain such a tiny object? Then in March 1802, Olbers made another discovery. A second small planet between Mars and Jupiter, which he named Pallas. Though slightly smaller, Pallas shared many similarities with Ceres, and their orbital distances were nearly identical. Soon after, more small celestial bodies were found. Juno, the third, and Vesta, the fourth. Astronomers began to revise their initial theory. Many now believed that this region of the solar system did not contain a single large planet, but instead was home to many small ones. Their suspicions were correct. Over the following years, thousands of similar small objects were discovered. To date, more than 4,000 such minor planets have been officially recorded. An estimate suggests that this region may ultimately contain up to 500,000 small bodies. These objects are all located in a specific region between Mars and Jupiter, a zone now known as the asteroid belt. Interestingly, the center of this belt lies exactly where the Titius-Bode law predicted a major planet should exist. On the one hand, astronomers marveled at how precisely mechanics and physics seemed to apply to our solar system. On the other hand, they were mystified. What force or event could have caused a single large planet to be broken into hundreds of thousands of fragments? One popular hypothesis was that a massive collision had occurred in this region. Experts believe that during the early stages of the solar system, collisions were both frequent and violent. Calculations even suggest that Earth was struck by a Mars-sized body known as Theia, and Mars itself may also have endured similar catastrophic impacts. Moreover, it is believed that the axial tilts of both Earth and Mars were also caused by massive collisions. Uranus, in fact, appears to have been completely knocked over by such an impact. It's essentially lying on its side along its orbital plane. In this sense, the cosmic traffic accidents of the solar system's early days remain vividly evident. However, these planetary collisions, although severe, were ultimately survivable, with each planet patched up over time. But what about the event that occurred in the asteroid belt? Could it have been the most catastrophic collision of all, one that shattered an entire planet beyond repair? Many experts believe this to be the case. It's possible that a super collision took place in this region, leading to the complete disintegration of a large celestial body. The 500,000 asteroids that now occupy the belt may well be the scattered remains, the ashes, of that lost world. Yet even if these asteroids are indeed fragments of a once large planet, there's a puzzling question. Why didn't they reassemble? After all, cosmic theories generally support the idea of planetary regeneration. Debris from destroyed planets is expected to eventually coalesce under mutual gravitational attraction and form a new celestial body. For example, it is widely believed that our moon formed from debris ejected by a colossal impact with the Earth. When the ejected material escaped Earth's Roche limit, the region where tidal forces prevent coalescence, it was able to clump together and gradually grow into a stable satellite, the Moon. Given that, and considering how closely packed the asteroids in the belt are, why haven't they formed a new planet over time? Experts suggest that the revival of a planet in the asteroid belt was actively prevented, and the culprit was its massive neighbor, Jupiter. Jupiter, the largest of all 8 planets in the solar system, possesses a mass 318 times that of Earth. Its enormous gravitational pull extends deep into the region of the asteroid belt. This immense influence has disrupted the orbital paths and mutual attraction of the asteroids, making it impossible for them to coalesce into a single planet again. There is concrete observational evidence of this disruption. Astronomers have discovered multiple gaps within the asteroid belt. Through calculations and analysis, scientists have concluded that these voids were created by Jupiter's gravitational resonances. These gravitational disturbances fractured the asteroid belt into distinct zones. These gaps are known today as the Kirkwood gaps, regions where Jupiter's gravity creates orbital resonances that eject or destabilize objects over time. Each gap corresponds to a different resonance ratio with Jupiter's orbit, further fragmenting the potential for unity in the asteroid belt. This graph illustrates the mean motion resonance patterns between the asteroid belt and Jupiter. The key resonance ratios include 3:1, 5:2, 7:3, and 2:1. Due to varying gravitational forces, the orbital speeds of asteroids within each gap differ. These variations lead to distinct gravitational resonances with Jupiter. It is precisely these misaligned resonances at different positions that cause the asteroids in the belt to move independently, preventing them from coalescing into a larger celestial body. Under Jupiter's influence, not only are the asteroids unable to form a single massive object, but the belt's high-density distribution and resonance disturbances also lead to frequent collisions. On average, for celestial bodies with a radius of 10 kilometers, a collision occurs approximately once every 10 million years. These impacts generate numerous asteroid fragments and lead to the emergence of new asteroid families. Within the asteroid belt, there are numerous such families, some with dozens of members, others with hundreds. In a simulated model of the asteroid belt, you can see these families represented by clusters of celestial bodies in different colors. These are known as asteroid families, and they are abundant within the belt. As a result, rather than growing larger through aggregation, the bodies in the asteroid belt tend to break down into smaller pieces over time. The asteroid belt contains 3 major types of asteroids based on composition: C-type, M-type, and S-type. In the inner region of the belt, S-type asteroids are more common. Spectral analysis reveals that these have metallic surfaces and are categorized as metallic asteroids. M-type asteroids, the second category, exhibit spectral lines indicative of iron and nickel content, placing them in the semi-metallic group. At the outer edge of the belt, C-type asteroids dominate. These are rich in carbon and are the lightest in mass among the 3. This orderly distribution appears to follow a gravitational filtering process, in which asteroids closer to the Sun tend to contain heavier metallic elements, while those further out are composed of lighter rocky materials. Over vast spans of time, these asteroids likely underwent orbital migrations and natural sorting based on composition. Though the asteroid belt may appear chaotic, in reality, it is a highly structured material zone. This compositional order greatly aids scientists in identifying and categorizing asteroids. Asteroids are remnants from the early formation of the solar system. Essentially, they are the fossils of our solar system. They record not only its history, but also some of its long-standing mysteries. Scientists are particularly interested in their composition. In 1991, the Galileo spacecraft en route to Jupiter flew past asteroid 951 Gaspra. During this flyby, at a distance of just 1,800 kilometers, humanity had its first close-range observation of an asteroid. On August 28, 1993, the Galileo spacecraft conducted observations of its second asteroid, 243 Ida. From a distance of about 2,400 kilometers, it captured images and performed multiple analyses. Ida is a potato-shaped asteroid approximately 56 kilometers long. Orbiting about 100 kilometers away from it was a small rock with a diameter of around 1.5 kilometers. This was the smallest and closest natural satellite to its primary body known in the solar system at that time. However, these observations were more like incidental visits rather than comprehensive explorations. The findings were not very in-depth or rich. It wasn't until February 17, 1996, that NASA finally decided to launch a dedicated probe for a full-scale investigation of an asteroid called Eros. The plan included having the spacecraft land on Eros in 2001. Eros is a near-Earth asteroid, meaning its orbit brings it relatively close to Earth. Scientists discovered that its perihelion, closest approach to the Sun, actually dipped inside Mars's orbit, coming as close as 22 million kilometers from Earth's orbit. At its aphelion, farthest point, however, it traveled well beyond Mars. This indicated a very unstable orbit, making it one of the most potentially dangerous asteroids to Earth. Researchers speculated that a similar asteroid, one with a highly eccentric orbit, might have been responsible for the mass extinction event that wiped out the dinosaurs 67 million years ago. In line with NASA's cost-saving strategies, the Near-Shoemaker, Near-Earth Asteroid Rendezvous mission was designed with a complex flight path. This avoided the need for an expensive heavy-lift launch vehicle. Since asteroids are small targets, the thinking was that the mission cost should be minimized accordingly. The Near-Shoemaker spacecraft launched on February 17, 1996. It used a gravity-assist trajectory, looping widely between Earth's and Mars's orbits to approach Eros. It passed by Eros twice, and by the time it finally rendezvoused with the asteroid in February 2000, it had already been traveling through space for 4 years. In contrast, a direct route would have taken only 1 year. Upon reaching Eros, the spacecraft patiently orbited the asteroid for about a year, conducting precise observations of this giant potato-shaped rock. Data transmitted back revealed that Eros has a surface covered with rubble and soil, remnants of 4.6 billion years' worth of collisions. These impacts, much like stir-frying, had broken large rocks into smaller debris and dust. Photos confirmed that new impacts were still ongoing. Infrared imaging revealed a large crater at the center of Eros, the result of a significant impact. Experts believe that Eros is a metallic-type asteroid, meaning it is relatively solid. If it had been a rocky-type asteroid, a collision of this magnitude might have split it in two. Ultimately, as planned, scientists directed the Near-Shoemaker probe to land on the asteroid. It descended from an altitude of 35 kilometers above Eros's surface, targeting a region known as Himeros. This marked the first successful landing of a human-made probe on an asteroid, a milestone with significant implications for the future of asteroid exploration and development. Meanwhile, Japan also initiated its own asteroid exploration project. The Japanese Space Agency launched a probe called Hayabusa, which means peregrine falcon in Japanese, aimed at exploring an asteroid named Itokawa. Like Eros, Itokawa is a near-Earth asteroid with an elongated elliptical orbit. Its perihelion is about 2.953 astronomical units, bringing it inside Earth's orbit, while its aphelion reaches approximately 1.695 AU, extending beyond Mars's orbit. With a total cost of $134 million, Hayabusa was one of the most economical deep space probes ever launched. It featured 4 highly efficient ion engines, which used ionized xenon gas as propellant. This allowed for long-duration space travel at much lower cost compared to conventional chemical propulsion systems, marking it as a new frontier in space exploration technology. One method involves altering the asteroid's trajectory. For instance, spacecraft could apply pressure or embed rocket-like devices into the asteroid's surface to produce thrust through reverse force, thereby shifting its path onto a new orbit. Some experts also propose using ultra-powerful infrared lasers. Modern lasers can concentrate immense energy and from tens of thousands of kilometers away can melt small celestial objects with high temperatures, slicing them into harmless fragments. Another strategy involves nuclear weapons. Humanity's nuclear arsenal is capable of destroying incoming asteroids. It can be said that we already possess a certain level of capability to protect ourselves from asteroid strikes, a capacity that will only grow stronger. At the same time, efforts to explore and utilize the vast resources of asteroids will intensify. Some believe that within the asteroid belt lie valuable mineral deposits essential to Earth. If humanity succeeds in exploiting these resources in the future, it could significantly advance our civilization. In short, asteroids are rare, scattered components of massive celestial bodies in the solar system. As our understanding deepens, so too will our knowledge of the solar system's material composition. Yet this vast universe is not just a field of dead orbits. Amidst the dazzling starlight lies a wondrous material world, a world in which life has emerged. To date, life has only been found on a single planet, Earth. It remains the only known cradle of life. But today, we understand more clearly that this cradle of life may not consist solely of Earth. It is a system composed of Earth and its satellite. Together, Earth and the Moon form a binary system, a shared cradle of life. Yet for a long time, we overlooked this crucial companion, the Moon. Modern science has proven that the Moon plays a significant role in the origin and evolution of life on Earth. This celestial body, the closest to Earth, whose mottled surface can be observed with the naked eye, is by no means an insignificant neighbor. Its presence has fundamentally altered the fate of our planet. However, no matter how much beauty and wonder the Moon once inspired in the human imagination, the scientific age has come at the cost of bidding farewell to mythology. After centuries of human inquiry, from the earliest telescopes to the lunar landers, we've come to understand that the Moon is fundamentally different from Earth. It is a lifeless, dry, and desolate world. The Moon is approximately 380,000 kilometers from Earth. Its diameter is 1/4 that of Earth, and its mass is just 1/80th. Because of its small size, the Moon's gravitational pull is too weak to retain an atmosphere. As a result, there is no air on the Moon. Naturally, without an atmosphere, there can be no life on the Moon. However, despite being lifeless itself, the Moon compensates for certain deficiencies of our life-bearing Earth. Beyond its overall gravitational influence on Earth's evolution, the Moon makes another critical contribution: its ancient, unchanging surface. Because the Moon is a relatively small celestial body with insufficient internal heat, its geological activity has remained extremely weak. As a result, its surface has barely changed for billions of years. This has allowed it to preserve, almost perfectly, a physical record of the early history of the solar system. In a sense, the Moon's surface serves as a unique form of oracle bones, a fossilized script offering direct insights into the solar system's distant past. Moreover, since the Moon is so close to Earth, its early history closely parallels Earth's own. In this way, the Moon compensates for the Earth's lost primordial record. The Moon's surface, especially its vast collection of impact craters, represents a preserved archive of the solar system's ancient legacy. Most of these craters are scars from meteorite collisions that occurred billions of years ago. Through the study of these craters, scientists have discovered that the early solar system experienced a relatively brief but intense period of meteor bombardment, lasting several hundred million years. These impacts can be seen as a kind of cosmic gift delivery, with each meteorite bringing different materials that enrich the planetary bodies. On Earth, early impact craters have long since been erased by active geological processes, a blurred and chaotic account. But on the Moon, whose geology is geologically lazy, these craters remain largely intact, preserving a snapshot of that ancient time. In this way, the Moon's cratered surface serves as a celestial memo, preserving the origins of spaceborne materials and possibly even clues about the early evolution of life that are now lost on Earth. Some of these ancient impact sites may even harbor secrets or chemical signatures related to life's early development that are no longer traceable on our own planet. Among these craters, however, there is a particular kind that appears to exert a more direct influence on Earth, the so-called rayed craters. Though often not very large in size, these craters have a remarkable ability to eject materials over vast distances. The dust and debris flung outward from these impacts can stretch for hundreds of kilometers, forming distinct patterns known as rays. The most iconic of these is the Tycho crater, which created a brilliant system of rays extending in straight lines from its center. Scientists consider this a lunar marvel. The rays' straight, unbent paths suggest a unique set of conditions. One is the Moon's low gravity, which allows dust to travel far. The other, more crucial factor is that the Moon does not rotate. Because the Moon does not rotate, it also lacks the Coriolis force, a phenomenon that cannot occur on Earth, which is a rotating planet. On Earth, any large-scale moving object, even in the absence of wind, will follow a curved path due to this rotational effect. Only on a non-rotating celestial body like the Moon can we observe such extraordinarily long, straight-line trajectories, a spectacle stretching nearly 2,000 kilometers. But why do some lunar craters have ray patterns while others do not? Experts believe the presence or absence of rays may be related to the thickness of the Moon's crust. In areas where the crust is thick, meteor impacts are less likely to eject substantial material. However, in regions where the crust is thin, collisions may trigger magma eruptions, possibly forming volcanoes. Today, we no longer see any active volcanoes on the Moon, and even moonquakes are extremely rare. The Moon is a planet with almost no geological vitality. Still, these ray systems offer clues that in its youth, the Moon did experience periods of geological activity. Some scientists suggest that volcanic eruptions on the Moon, aided by its low gravity and lack of atmospheric resistance, could have propelled material to extraordinary heights and distances, potentially even sending some of that material to Earth. It is possible, then, that lunar substances contributed to the evolution of life on Earth. Could it be that these radiant patterns on the Moon not only serve as beautiful remnants of its explosive past, but also hint that our genetic legacy carries traces of these celestial fireworks? The Moon's last volcanic activity, its final fireworks, occurred around 3.5 billion years ago. Since then, it has seemingly fallen into a deep slumber, with barely any movement detectable. Yet this sleeping position is quite peculiar. The Moon always presents the same face to Earth, locked in place by Earth's gravitational pull. Interestingly, the side facing Earth is also its youngest, what we refer to as the lunar belly, known as the lunar maria. These seas are not water, but expansive plains formed by ancient lava flows. Typically, lava results from volcanic eruptions, but on the Moon, there are no visible volcanic vents at the edges of these flows. This has led some scientists to hypothesize that as the Moon cooled, its outer shell contracted, causing the crust to crack in places. Magma from beneath then flowed out through these fissures, spreading across the surface and forming the lunar maria. Because this lava surfaced relatively late in the Moon's geological timeline, fewer impact craters formed atop these plains, making them the most recent flooring on the Moon. But why do all the maria face Earth? Some researchers suggest this is due to the roly-poly effect. The Moon, like a weighted toy, gradually adjusted its orientation until its heaviest side, the one with the dense maria, faced downward toward Earth. Earth's gravity then locked it in this position. The lava that forms the lunar maria is primarily basalt, a dense volcanic rock. As the moon's rotation gradually slowed, the heavier side, weighted by these basaltic plains, ended up facing Earth. However, there is another theory. The far side of the moon is more prone to meteorite impacts. According to a mechanical principle known as the transmission effect, the force waves generated by impacts on one side of a celestial body may manifest on the opposite side. Earth provides a possible example of this. There is evidence that a meteorite impact in Africa was followed almost simultaneously by a volcanic eruption in Hawaii, nearly on the opposite side of the globe. In a similar way, the Maria on the moon's near side might actually be surface scars resulting from powerful impacts that struck the far side. If this theory proves correct, then the moon has acted as a sacrificial shield for Earth, absorbing blows that could have otherwise devastated life here. Its molten plains stand as silent reminders of the protection it has offered, a debt of gratitude that Earth's living beings may forever owe. Yet despite its quiet presence and apparent role as Earth's protector, the moon's existence becomes increasingly mysterious the more we study it. In some respects, the moon is a rather terrifying orbital companion. Its size relative to Earth is unusually large. According to the principles of celestial mechanics, gravitational attraction between two sizable bodies should pull them closer together over time, ultimately causing them to collide. When we examine other planets in the solar system, like Jupiter and Saturn, we notice that although they are far larger than Earth, their moons are roughly the same size as ours. This makes Earth's moon anomalously large. Normally, celestial bodies have a built-in safety buffer called the Roche limit, a boundary within which the tidal forces of a massive object can tear apart a smaller one due to differential gravity. When a smaller body crosses within this limit, the gravitational pull from the larger one can deform and eventually break it apart, a process known as tidal disruption. However, the Roche limit has its limits. If the smaller body is large and structurally strong enough, it can resist these tidal forces. Given its size, the moon technically exceeds Earth's Roche limit. It has crossed that invisible boundary and should, by all logic, be moving closer, with the potential for eventual collision. This was once considered a serious possibility. However, current calculations show the opposite. The moon is actually drifting away from Earth. Measurements indicate that the moon recedes at a rate of about 3 centimeters per year. Why is this happening? This apparent violation of typical orbital dynamics? Scientists believe it may be the result of an extremely rare phenomenon in the cosmos. Earth's unique surface composition could be playing a role. This is because Earth is a planet covered in liquid water. Over 70% of Earth's surface is water, and under the gravitational pull of the moon, this vast amount of water behaves differently than the solid land masses. As the moon passes over the Earth, it pulls on the water, creating a slight lag compared to the rotation of the land. This friction between the water and land gradually slows Earth's rotation. According to the law of universal gravitation, gravitational interaction between celestial bodies depends not only on mass, but also on their rotational angular velocity. As Earth's rotation slows, the centripetal force it exerts on the moon decreases. As a result, the moon gradually moves farther away. This shift in orbital distance has been occurring over the last 4 billion years. From this, we know that the moon has been slowly drifting away from Earth. Today, it is about 380,000 kilometers away, but 4 billion years ago, the moon was just tens of thousands of kilometers from Earth. In a sense, it was water that saved Earth, not only by giving rise to life, but also by preventing a catastrophic collision with its oversized orbital companion. So, when we observe the ebb and flow of the tides, we should also give thanks to this miraculous substance. It not only nurtures life, but has also helped our planet avoid total annihilation. This phenomenon is uniquely Earth's, as no other known planet in the universe possesses liquid water on its surface, at least not yet discovered. But if the moon is now moving away, it must have once been much closer. Based on its current rate of recession, we can estimate that 4 billion years ago, the moon was essentially clinging to Earth. This raises a puzzling question. Given the existence of tidal forces, how could two massive bodies have ever been that close? This conundrum has led many scientists to favor a bold and astonishing hypothesis, that the moon originated from Earth itself. It was once part of our planet, then separated and was gradually pushed outward. Only this scenario makes the moon's existence and behavior comprehensible. This seemingly unbelievable theory has gained further support through direct sample analysis. When scientists compared samples from the moon with Earth rocks, they discovered that their isotopic compositions, particularly those of oxygen, are nearly identical. The ratios of oxygen-16, oxygen-17, and oxygen-18 in lunar samples are strikingly similar to those found on Earth. These elemental ratios function like a barcode, an extremely precise fingerprint. No matter how surprising it may be, the evidence is clear. Like a parent and child, Earth's vibrant living landscapes and the moon's barren, desolate plains are made from the same original materials. In contrast, the isotopic composition of other celestial bodies in the solar system differs significantly from that of Earth. This further supports the idea that the moon was once part of Earth. However, through the observation of numerous moonquakes, scientists have learned something peculiar about the moon's interior. When seismic waves travel through its layers, they reveal that the moon's core is very small. Since the core is composed of heavy metals, a smaller core suggests that the moon lacks such materials. This makes the moon significantly less dense than Earth, nearly half as dense. This tells us that although the moon shares Earth's DNA and may have originated from it, it was formed primarily from Earth's outer layers, not its metal-rich interior. So what kind of force could have precisely sliced off this outer shell, as if peeling the skin off an apple? Many researchers, after synthesizing all available evidence, believe that a massive impact is the most likely explanation, but only if the collision occurred at a very precise angle. This hypothesis suggests that around 4.5 billion years ago, during the early formation of the solar system, Earth was accompanied by a Mars-sized protoplanet, often referred to as Theia. Theoretically, both planets had the potential to host life, but their close proximity meant coexistence was unsustainable. A merger was inevitable. And so, a colossal impact took place. Theia crashed into Earth in a dramatic collision, a scenario supported by advanced computer simulations that recreate the physics of such an event. Theia struck Earth at an angle of approximately 45 degrees. The impact shattered Theia and partially pulverized Earth's outer layers. This collision also caused Earth to begin spinning rapidly and ejected enormous amounts of material from Earth's crust into space. These ejected materials, hot, molten, and vaporized by the intense energy of the impact, formed a vast cloud encircling Earth. It was from this debris that the moon eventually formed. Let's visualize this moment. Theia crashes into Earth from the side at a velocity of around 5,000 kilometers per hour, fast enough to rip open Earth's crust. The cores of Earth and Theia merged, forming a larger, unified iron core at the center of our planet. Meanwhile, a significant portion of Earth's outer shell was blasted into space. The tremendous heat generated by the collision vaporized the ejected crustal material, which spread outwards and began to orbit Earth in the form of a debris cloud. As this vaporized material cooled, it condensed into rock, forming a disk around Earth. However, this rock disk initially lay within Earth's Roche limit, the region where tidal forces are so strong that any large object would be torn apart. Within this zone, the debris could not coalesce into a single large body. Instead, the particles repeatedly collided, causing shock waves that drove material outward. Once the ejected rocks moved beyond the Roche limit, they were no longer bound by Earth's tidal forces. Freed from this gravitational constraint, the rocky debris could begin to coalesce through repeated collisions, gradually merging and rapidly growing. This marked the birth of the moon. Roughly a year later, a fully formed moon, about 3,500 kilometers in diameter, emerged at a distance of approximately 30,000 kilometers from Earth. Today, we can reasonably conclude that the moon's material originated from Earth. The rocks and dust that formed it once lay close to our planet. However, for the moon to take shape as a complete celestial body, it had to form beyond 34,000 kilometers from Earth, the outer boundary where the Roche limit ceases to exert its destructive effect. In other words, Earth's no-build zone in space extends up to 34,000 kilometers. Within this region, Earth's gravitational field prevents the stable formation of any sizable body. Therefore, the closest distance the moon could have formed from Earth is just beyond this boundary. That means the moon, even after its formation, remained a potentially dangerous neighbor, much like its predecessor Theia. It could, in theory, be pulled back by Earth's gravity and collide again. But Earth had changed. After the impact, it began spinning rapidly. This rotation played a major role in generating tidal forces, and tidal forces gradually pushed the newly formed moon farther and farther away from Earth. Over time, the moon drifted outward. The moon's formation was largely complete about 4.5 billion years ago, as evidenced by the age of its oldest rocks. Earth's first life, on the other hand, is believed to have appeared around 4 billion years ago. This means the moon existed before life began on Earth. Scientists believe the moon did more than simply witness the birth of life. It may have been instrumental in creating it. Its influence on life's emergence and evolution has been far greater than previously imagined. The universe is a highly standardized material system. Its products, stars, planets, moons, tend to follow uniform patterns. Life, however, is a non-standard phenomenon. Amid the brilliance of the stars, life remains extraordinarily rare. One could say that for life to emerge on Earth, the cosmos had to summon every bit of chance, coincidence, and fortune available within its material framework. To date, the solar system is the only place known to host life. Even after 4 billion years of evolution, this great construction site of living brilliance still stands, largely intact. And we can still observe the ancient foundations laid for the transformation of dust into living matter. Here lies a star, stable, with a mild temperament, capable of burning for 10 billion years, providing consistent and abundant energy. Surrounding it are 8 planets, each representing a different type of celestial body. Scientists believe that this diversity of planetary types significantly increases the chances for life to emerge. In this sense, the solar system is not just a cradle for life. It is a carefully balanced system designed, in its own accidental way, to give life a fighting chance. Even if the birth of life is a matter of luck, the universe appears to have made a selective bet. It chose the best possible location and duplicated 2 nearly identical planets, Earth and Venus, in what it deemed the most promising spot for life to arise. In hindsight, the universe's wager was successful. Life did emerge on one of these twin planets. But this raises a profound question. If Earth and Venus share such striking similarities, why did life choose Earth and not Venus? Today we know that while the 2 planets have much in common, there is one often overlooked but critical difference. Earth has a moon and Venus does not. This seemingly minor distinction is now believed to be a crucial reason Venus failed to support life. Many scientists now believe that the moon was an essential part of Earth's life project, the startup system that made life possible. Without the moon, Earth might never have developed life at all. In fact, we can think of both Earth and Venus as life factories, perfectly equipped with the right components. But for a factory to begin operation, it needs electricity. Without power, even the most advanced systems cannot function. So, how do planets get powered up? They cannot plug into an external source, of course. Fortunately, both Earth and Venus have built-in generators, thermal power plants at their cores. At the center of each planet, temperatures exceed 6,000 degrees Celsius. At such extreme heat, the metallic iron in the planetary core becomes plasma. And when plasma rotates, it generates electric currents. But only Earth ended up generating electricity. Venus did not. What powered Earth's generator was a collision. the same one that created the Moon. A Mars-sized protoplanet struck Earth at just the right angle, setting the planet spinning. That spin activated Earth's internal dynamo and turned it into a working generator. Venus, it seems, never experienced such a collision. Its generator was never switched on, and so the destinies of the two planets diverged. The most vital function of this internal power system is the generation of a magnetic field. A planet capable of hosting life must reside near its parent star, otherwise it would not receive enough energy. But proximity to a star is dangerous, like trying to bargain with a tiger. While a planet gains energy, it also faces deadly threats from the star, especially in the form of harmful solar radiation. Among the most dangerous solar emissions are charged particles. These can severely damage the delicate molecules needed for life. That's where a magnetic field comes in. It acts as a planetary shield, protecting against these charged particles. Earth's magnetic field forms a protective barrier roughly 64,000 kilometers above the surface. It filters harmful radiation while still allowing sunlight to pass through. The Earth's magnetic field not only shields life from solar harm, it also protects one of life's most essential ingredients: liquid water. Water molecules, made of 2 hydrogen atoms and 1 oxygen atom, are vulnerable to the sun's charged particles. When struck by these energetic particles, the chemical bonds can be broken, splitting the molecules apart. Once separated, the light hydrogen atoms can escape Earth's gravity and drift into space. Without the ability to reconstruct those water molecules, Earth would gradually lose its water reserves. But thanks to the magnetic field, as water vapor rises into the atmosphere, this electromagnetic sealing blocks the destructive solar particles. This means Earth's water vapor can remain safely within the planet's atmosphere, perpetually cycling between land and sky in a stable hydrological loop. In truth, the Moon is Earth's largest investor, or rather, a shareholder in this planetary water economy. It is the byproduct of a cosmic collision, sacrificing half its original mass as an investment. In return, it gave Earth its high-speed rotation, which powers the internal dynamo that generates Earth's magnetic field, the very shield that protects liquid water. In Earth's early days, surface temperatures were blisteringly high. Rain could not even reach the ground before it evaporated. But in the upper atmosphere, under the protection of the magnetic field, water vapor could cool and eventually fall again as rain. This cycle continued endlessly until at last the rain reached Earth's surface. The rainfall in that era was far greater than what we see today, as surface evaporation occurred at an immense rate. Thick, dark clouds, filled with volcanic ash and moisture, likely covered the sky and unleashed torrential rain for tens of thousands of years without stopping. It was this deluge that carved the first oceans onto Earth's surface. And within those oceans, the most important event in the history of the universe occurred: the birth of life. In liquid water, simple molecules had the opportunity to combine in increasingly complex ways. At the pinnacle of this complexity, life emerged. Around 4 billion years ago, a group of remarkable molecules in an energy-rich, liquid water environment began a long and arduous journey. After countless trials and failures, they finally succeeded in creating life. And now, 4 billion years later, the descendants of those primitive, microscopic particles, which were far simpler than even the most basic cells, would go on to dominate the planet. Among them, one line would eventually become us, human beings. But from the birth of life to the evolution of humans, Earth's biosphere would need another 4 billion years of continuous transformation. That journey has been unimaginably long. Yet, scientists believe this time frame has already been greatly shortened, accelerated by a chain of favorable conditions. Under Earth's current dynamics, if evolution had taken its natural course without those early boosts, it might have been delayed by more than half. One of the greatest constraints on the pace of evolution has always been access to solar energy, because life depends on sunlight to survive. Ultraviolet radiation was once extremely lethal to life. Fortunately, this issue has been resolved in the modern era thanks to the abundance of green plants on Earth. These plants are capable of producing over 10 trillion tons of oxygen, making up about 25% of the atmosphere. When exposed to sunlight, this oxygen transforms into ozone, which in turn reflects ultraviolet rays back into space. However, in the early Earth, oxygen was scarce, and the ozone layer had not yet formed. Without this protective shield, ultraviolet radiation bombarded the planet's surface without resistance. Early life, having no other option, had to adapt to this hostile environment by dividing its activities into day and night shifts. The destructive effects of ultraviolet rays were most apparent during cell division, when exposed DNA and proteins were most vulnerable. To survive, primitive cells scheduled photosynthesis for the daylight hours and reserved reproduction for the night. In this way, early life used the natural cycle of day and night as a switch to regulate growth and reproduction. But because this switch only operated once per cycle, the pace of day and night transitions essentially determined the speed of biological evolution. Fortunately, the Earth's rotation in those ancient times was much faster than it is today. Current scientific calculations show that Earth's rotation is gradually slowing down, lengthening by about 1.6 seconds every 100,000 years. Based on this, it is estimated that around 4 billion years ago, Earth's rotation was about 6 times faster than it is now. This means that the cycle of day and night was 6 times shorter, and the rhythm of life moved at an accelerated pace. In a sense, the Moon was born out of a near-suicidal planetary collision, and it was that violent impact that gifted Earth its astonishing early spin. That rapid rotation acted as a powerful engine, driving the biological clock and speeding up the evolution of life on our planet. This model of Earth's rotation reveals how the planet's spin has slowed over different geological periods. Our simple ancestors lived through a much more intense biological tempo than we experience today, but that speed was necessary. While the Sun is an exceptional nuclear furnace with a theoretical lifespan of about 10 billion years, its prime operational period only lasts around 6 to 7 billion years. After that, its nuclear fuel will gradually deplete, leading to a massive expansion. Eventually, the Sun's fire will engulf the inner planets, including Earth. Experts believe that Earth's rapid early rotation drastically shortened the time needed for life to evolve, allowing us to now enjoy the benefits of solar energy without the looming pressure of time. This acceleration also helped minimize the risks that could have emerged if evolution had taken longer. Yet, the story of life is not merely one of speed. As organisms grew more complex, they began to require more stable and dynamic conditions from Earth. At that crucial point, the Moon, still playing its role as a legacy of that ancient impact, became a key force in shaping the destiny of life on this planet. The Moon, on one hand, acts as a brake for the Earth, gradually slowing its rotation and bringing greater calm to the planet's surface. At the same time, it plays a vital role in preventing disasters caused by Earth's internal energy. We know that Earth operates like a giant generator, producing a strong magnetic field that perfectly shields the planet. This magnetic field helps Earth stay warm as it orbits the Sun and safeguards both life and water resources on the planet. However, this magnetic shield is a double-edged sword. While it protects us from external threats, it also brings internal risks. Earth is a planet with immense internal heat. Without such heat, the magnetic field would not exist in the first place. But this heat cannot remain trapped underground forever. Sooner or later, it must find a way to escape to the surface. If left unchecked and allowed to accumulate, this energy would eventually erupt through massive volcanic explosions, causing widespread devastation and unimaginable consequences for life on Earth. Oddly enough, Earth does not have many large volcanoes. Compared to its planetary neighbors, Venus and Mars, Earth has far fewer and generally smaller volcanoes. Venus, for example, is dotted with about 100,000 volcanoes, covering nearly its entire surface in searing lava. Mars, while not as volcanic in quantity, hosts some of the largest volcanoes in the solar system. Its Olympus Mons is nearly 3 times taller than Mount Everest, Earth's highest peak. A single eruption from such a volcano could engulf half of Mars. In contrast, Earth's volcanoes are modest in size and limited in number. Most of them are arranged in a highly orderly manner along narrow boundary lines between continents and oceans. Scientists believe this too is due to the moon. In a very real sense, the moon acts as Earth's firefighter, playing a key role in stabilizing tectonic activity. It enables the movement of Earth's continents, what we now call plate tectonics. These movements are essentially heat release mechanisms unique to Earth. No other planet shows this dynamic behavior. For a long time, scientists were puzzled about the origin of this phenomenon. Today, many scholars believe the moon plays a central role in it. This is because the moon exerts a powerful tidal force on Earth's water. This gravitational pull not only creates the familiar ocean tides, but also sets large-scale fluid dynamics into motion. These movements, through a mechanism akin to a seesaw, apply fluctuating pressure on Earth's crust. As the tides rise and fall, they exert constantly changing forces on the crust beneath. This repetitive stress causes the crust to fracture and shift over time. As a result, tectonic plates move, and vast amounts of energy are released at their boundaries. This release of heat prevents dangerous pressure buildup beneath the Earth's surface. In other words, by triggering and guiding controlled destruction of the crust, the moon helps maintain surface tranquility. Through this quiet yet profound influence, the moon ensures that Earth's inner turmoil does not erupt into catastrophic chaos, allowing life to thrive in peace on the planet's surface. Some experts believe that the moon's influence on Earth's tectonic plate movements is not limited to mitigating natural disasters. It has also played a critical role in the evolution of life. Once upon a time, Earth was dominated by a class of colossal animals, the dinosaurs. During their reign, the continents were fused into one giant landmass known as Pangaea. Dinosaurs lived on this vast supercontinent, which lay predominantly along the equator and maintained a consistently warm climate. As cold-blooded creatures dependent entirely on solar energy, dinosaurs thrived in this warmth and ruled the Earth for nearly 200 million years. In that time, they evolved into majestic forms, massive bodies composed of fat and protein. The tallest dinosaurs could reach up to 40 meters, towering like living skyscrapers built of biological material. Yet Earth refused to allow life to remain merely a grand accumulation of protein and fat. Life was meant to have richer complexity. With the moon's assistance, the land masses began to shift. About 200 million years ago, Pangaea started to break apart. This continental drift marked the beginning of the end for the dinosaurs. Experts believe that some of the drifting landmasses migrated toward the poles, where they became snow-covered and formed ice sheets. In effect, this was akin to installing air conditioning for the planet, resulting in a substantial drop in global temperatures. The dinosaurs, once overly pampered by a warm climate, could not adapt to this sudden cooling. Gradually, they went extinct. In their place rose mammals, species equipped with internal heat generation systems and far better suited to handle harsh, fluctuating climates. Mammals began to flourish, and with their success, the clock toward human emergence began to tick. Continental drift not only allowed mammals to replace dinosaurs, but according to recent findings, it may also be closely linked to the very origin of humankind. While the consensus remains that humans evolved in Africa, some researchers believe that the seeds of humanity, that is, the earliest higher primates, may have originated in eastern China, in the region of Liang, Jiangsu province. In an unremarkable limestone quarry in Liang, scientists discovered several tiny yet significant fossilized teeth. Though small, these teeth were verified by experts to belong to the earliest known higher primates on Earth, dating back some 45 million years. This discovery extended the timeline of our evolutionary ancestors beyond what was previously known in Africa and filled in a crucial missing link. That very gap, once elusive, was now bridged by these fossils. The early primate was named Eosimius sinensis, or dawn monkey of China. Although its facial reconstruction differs greatly from modern primates, resembling more of a cat than a monkey, Its cranial and oral structures, the most defining features, aligned closely with the traits of higher primates. One especially notable feature was its shortened anterior premolars, significantly reduced compared to those of lower primates. Its facial flatness had also reached a level quite close to modern higher primates. Because of these traits, it is now considered the earliest known higher primate on Earth. As this ancient primate, the seed of humanity, was thriving in Asia, a dramatic geological event unfolded. The Indian subcontinent collided with the Eurasian landmass. This monumental impact completed the final puzzle piece of today's world map and set the stage for the next chapter in Earth's evolutionary story. This monumental collision between tectonic plates created a great passage between Asia and Africa. Experts believe that it was likely during this period that Eosimius sinensis, the dawn monkey of China, began its migration toward Africa, setting the stage for the next, more spectacular chapter in human evolution. Today, researchers are actively searching for the possible route that Eosimius might have taken to reach Egypt, the potential migratory path that led to the rise of humankind. Although many details still require further evidence and analysis, the shifting geological environments created by Earth's plate tectonics supported the different evolutionary stages of early humans. It is now believed that perhaps the joint effort of the Asian and African continents ultimately enabled the birth of humanity. If the movement of the continents was indeed intricately linked to the gravitational influence of the moon, then the moon must be recognized as an indispensable actor in the emergence of human life. We can now confidently say that the cradle of life was not merely Earth alone, but a system jointly formed by Earth and its moon. Today, with the natural evolution of life largely complete, the moon has fulfilled its original mission. But looking forward, what new contributions might it offer humanity? Without a doubt, exploring and developing the moon will be a monumental leap for humanity's journey into space. The moon holds tremendous significance for our future, especially in solving one of the most pressing problems we face on Earth: energy. Humanity must eventually move beyond our dwindling supply of fossil fuels and embrace highly efficient, clean energy alternatives. Chief among these is nuclear fusion. Yet the fuel needed for fusion is rare and costly on Earth. The moon, however, is a veritable treasure trove of fusion fuel. For billions of years, it has collected vast amounts of charged solar particles, particularly helium-3, a potential fuel for fusion. These particles are typically deflected by Earth's magnetic field to protect life and water resources. But the moon, lacking such a magnetic shield, has absorbed them freely for eons. Today, its surface is coated with millions of tons of solar-charged particles, more than enough to power humanity for centuries. From this perspective, the moon's future value to human energy needs may equal or even surpass the role that oil from the Middle East plays today. Beyond energy, the moon is also rich in mineral resources. Many of these materials were delivered by meteorites and remain scattered across the lunar surface. Because the moon has no tectonic activity, these deposits have remained largely undisturbed, preserved in place for billions of years. The moon, in essence, is a 4-billion-year-old cosmic mineral supermarket. Humanity has already begun exploring its surface, and it is widely believed that these efforts will yield abundant rewards. Notably, ice has been discovered in the moon's polar regions, an immensely significant finding for future lunar development. This vital resource could support the establishment of a sustainable lunar ecosystem, facilitate human settlement, and greatly advance the broader exploitation of the moon. Beyond ice, the moon harbors numerous other resources essential for the continued progress of human civilization. Some have even predicted that the next great leap in technological advancement will occur on the moon. It is becoming increasingly clear that the era of large-scale lunar development is fast approaching. Our solar system is not only a cradle of life, it is also a masterpiece of cosmic engineering and aesthetic symmetry. While we don't yet know whether such a structure is necessary for life to emerge, it is evident that the solar system that nurtured us is uniquely organized. there are 8 major planets. 4 rocky planets, including Earth, orbit close to the Sun and are known as the inner planets. The remaining 4, massive gas giants, reside in the outer solar system and are referred to as the outer planets. These outer giants, Jupiter, Saturn, Uranus, and Neptune, are not only vast in size but also precisely spaced in their orbits. Both the inner rocky planets and the outer gas giants follow a distinct geometric distribution, each orbiting at proportional distances. This orderly configuration raises important questions. Is our solar system's structure a rare design, or is it a common pattern throughout the universe? Further exploration is needed to uncover the answer. Nevertheless, many experts believe that the arrangement of our solar system may be closely tied to the emergence and evolution of life on Earth. Among the outer planets, the one closest to us is Jupiter, located approximately 800 million kilometers from the Sun. Jupiter is remarkably bright in the night sky. In Roman mythology, it was considered the king of the gods, Jupiter or Jove. In ancient China, it was known as the year star, Suxing, as early observers noticed that it takes roughly 12 Earth years for Jupiter to complete a single orbit around the Sun. In that same time, Earth orbits the Sun 12 times. From our perspective on Earth, Jupiter's position in the night sky shifts each year, returning to the same place only after a full 12-year cycle. As a result, ancient scholars divided Jupiter's celestial journey into 12 parts, a system that would later influence aspects of astronomy, astrology, and timekeeping in various cultures. This 12-year orbital cycle of Jupiter was divided into 12 segments, known as the 12 branches. Each year, as Jupiter passed through one of these divisions, the position it occupied was used to name that year. This system of year naming was known as the Jupiter cycle calendar, Suing Jinian, and it played a significant role in ancient Chinese chronology. Jupiter is the largest planet in the solar system. Its diameter is about 11 times that of Earth, and its mass is approximately 300 times greater. In fact, Jupiter's mass exceeds the combined mass of all the other planets, moons, asteroids, and celestial bodies in the solar system, excluding the Sun. Studies have shown that Jupiter is primarily composed of hydrogen, which makes it structurally similar to the Sun. Hydrogen is the most reactive and fusible element in the universe. It accounts for over 95% of all known matter in the cosmos. It is this abundance of hydrogen that gives rise to the radiant starlight across the night sky, as countless nuclear fusion reactions illuminate the universe. Our Sun, for instance, is a fusion-powered celestial body with a core temperature of tens of millions of degrees Celsius. Within our solar system, the Sun reigns as the largest object. It is roughly 10 times the diameter of Jupiter and has a mass about 1,000 times greater. Though Jupiter resembles the Sun in composition, it lacks the mass required to become a star. To ignite nuclear fusion like the Sun, a celestial body needs at least 8% of the Sun's mass. Jupiter, however, has only about 0.1% of the Sun's mass. To reach the threshold needed to shine like a star, it would need to increase its mass nearly 8-fold. Despite this, Jupiter's immense internal pressure still generates considerable heat. Its internal temperature is estimated to reach around 30,000 degrees Celsius. Remarkably, this internal heat output exceeds the amount of heat Jupiter receives from the Sun. While the average temperature of space surrounding Jupiter is about -170 degrees Celsius, Jupiter's upper atmosphere maintains a temperature of around 150 degrees Celsius, 20 degrees warmer. This suggests that Jupiter operates its own low-cost heating system, driven by its massive internal energy. Of course, this is merely a surface-level manifestation of the planet's immense internal power. Outwardly, Jupiter appears calm and subdued, not revealing the astonishing nuclear potential hidden within. To understand Jupiter's interior more deeply, scientists launched the Galileo spacecraft in 1995. One of its missions was to send a probe directly into Jupiter's thick atmosphere and collect data until it disintegrated from heat and pressure. On December 7, 1995, the Galileo atmospheric probe plunged into Jupiter, the solar system's largest planet, and successfully transmitted valuable data. Though the mission was brief and suicidal in nature, it provided groundbreaking insight into Jupiter's inner energy systems. As the probe descended through the atmosphere, it encountered extreme turbulence, storms, lightning, and massive atmospheric disturbances, all indicating constant unrest and energy release from within. These storms dwarfed any weather systems on Earth. After 57 minutes, the probe was finally destroyed by the immense heat generated by friction within Jupiter's violent atmosphere. But in that short time, it had already sent back enough information to confirm the planet's vast internal energy and dynamic turbulence. Some scientists believe that although Jupiter's current mass falls far short of the requirements for becoming a star, its behavior and energy output suggest a latent potential, one that makes it a failed star, but one still brimming with cosmic significance. But perhaps, in the distant future, billions of years from now, when our current sun begins to die and expands into a red giant, it may shed vast amounts of material into the solar system. If that happens, Jupiter could potentially capture some of this ejected solar matter, increasing its own mass. And if Jupiter's mass surpasses a critical threshold, it may one day ignite and become a new star. At that point, it could possibly replace the Sun, continuing to supply energy to the solar system as its second sun. The second largest planet in the solar system is Saturn, located about 1.4 billion kilometers from the Sun, roughly 600 million kilometers farther out than Jupiter. Saturn is smaller than Jupiter, though only slightly in volume. However, in terms of mass, it is significantly lighter, only about one-third the mass of Jupiter. Saturn's most iconic feature is its magnificent ring system, which makes it the most beautiful planet in the solar system. These rings encircle the planet's equator, stretching from about 6,630 kilometers above Saturn's surface to as far as 120,700 kilometers. Though the rings span roughly 120,000 kilometers in width, they are astonishingly thin, on average only about 20 meters thick. The rings consist of countless tiny ice particles and fragments that orbit Saturn in a single flat plane. These icy chunks range in size from just a few centimeters to several dozen centimeters, with only a few pieces exceeding a meter in diameter. Within Saturn's ring plane, there are hundreds to thousands of distinct ringlets, each varying in size and shape. For many years, scientists believed Saturn's rings were relatively young, formed just about 100 million years ago, perhaps in a single event when a comet collided with one of Saturn's large moons. But recent studies suggest a more complex origin. It now appears that the various rings differ greatly in age, with some possibly forming over 1 billion years apart. This has led to growing acceptance of a new explanation involving the Roche limit, a critical boundary around a planet. Within this zone, a large celestial body's gravitational pull becomes strong enough to tear apart smaller objects that come too close. Scientists now believe that Saturn's rings likely formed when asteroids or comets entered this Roche limit at different times and were torn apart by Saturn's gravity. Why then does Saturn have such a prominent ring system, while the other gas giants do not? Many experts suggest the answer lies in Saturn's unique density. Among all the planets in the solar system, Saturn has the lowest density. In fact, if there were an ocean large enough, Saturn could float on water. Because of this low density, the material on Saturn's surface has a similar specific gravity to that of the ring particles. This may explain why the rings have remained stable and prominent around Saturn, whereas similar debris around other gas giants may have dispersed or failed to coalesce into such a visible system. Uranus's appearance among the planets is truly unique, particularly due to the extreme tilt of its rotational axis. With an axial tilt of approximately 98 degrees, Uranus essentially lies on its side as it orbits the Sun, its axis nearly parallel to the orbital plane. Why does Uranus have such a dramatic tilt? Most scientists believe that at some point in its past, Uranus experienced a massive collision with a large celestial body. The force of this impact was so great that it flipped the entire planet over. However, many experts also suggest that this event likely occurred when Uranus was still relatively small in size. Otherwise, it's hard to imagine a body large enough to knock over the Uranus we know today. In other words, Uranus may have a history of having been bullied, but it has since grown into a true planetary giant. Neptune is the fourth gas giant of the solar system and is currently the farthest planet from the Sun. It lies at a distance approximately 30 times farther from the Sun than Earth does. At that great distance, only faint traces of sunlight reach its atmosphere, making it a darker and colder world. Neptune is the third largest planet by volume in the solar system, slightly smaller than Uranus in size, but significantly more massive. Through telescopes, Neptune appears as a bright and vivid azure sphere. Its captivating color is part of the reason it was named after the Roman god of the sea. Like a blue pearl gleaming in the depths of space, Neptune glows with a quiet, mysterious brilliance. The planet's blue appearance is like Uranus's, largely due to methane in its atmosphere. Methane absorbs red light, allowing blue wavelengths to dominate. Neptune's atmosphere consists of roughly 85% hydrogen, 13% helium, and about 2% methane. This is nearly identical to Uranus, but Neptune contains a slightly higher amount of ammonia. This seemingly minor difference may be what gives Neptune its deeper, purer blue hue. In many ways, these two outermost blue planets of the solar system can be seen as products of the cold industrial process of the cosmos. They are perhaps the solar system's most efficient recycling of leftover debris, cosmic refuse transformed into major planetary bodies. Despite being made from the remnants of solar system formation, these waste-collecting giants have proven to be immensely valuable. Not only are they worthy of study in their own right, but it is also possible that deep within their mysterious interiors lies organic matter, potentially life-related compounds, that could offer new clues about the origins of life itself. Even more importantly, every large celestial body added to the solar system's outer orbital regions contributes to the security of Earth. The presence of these giant planets helps stabilize the gravitational dynamics of the solar system, deflecting or capturing rogue asteroids and comets that might otherwise pose threats. Although gas giants and rocky planets might seem to belong to two separate planetary systems, scientists now believe there is a deep, interconnected relationship between them. For early Earth, the delivery of external material through comets, asteroids, and other space debris was crucial to its development and possibly the very origin of life. Comets and asteroids contain many materials that are rare or absent on Earth. During Earth's early years, the frequent visits of comets and asteroids enriched the planet's resources, laying the groundwork for the emergence of life by providing vital materials. However, once life appeared, and especially once it reached more advanced stages, such frequent cosmic air raids became far too dangerous. History has already shown how catastrophic a single impact can be. One asteroid strike is believed to have wiped out the dominant species of its time, the dinosaurs. If such events had happened repeatedly, it's hard to imagine the devastating toll on Earth's biosphere. Fortunately, Earth is relatively safe today, in large part because the solar system contains comparatively few roaming celestial hazards. Much of this safety is thanks to the four giant planets, which act as guardians, eliminating or deflecting potential threats before they reach Earth. When we say there are fewer dangerous celestial bodies in the solar system, we're really saying the solar system has been well cleaned, and we owe that to Jupiter, Saturn, Uranus, and Neptune. These giant planets serve as both bulldozers and janitors of the solar system. Within their gravitational domains, they do not tolerate debris. They sweep their orbital paths clean, swallowing or flinging away any fragments or comets that venture too close. Imagine if those giant planets weren't there to regularly clean their regions. Their orbital zones might be overrun with stray comets and fragmented bodies. In such a chaotic system, Earth would be at much greater risk of catastrophic impacts. We already see a cautionary example between Jupiter and Mars, the asteroid belt. This region lacks a large planet to dominate and stabilize it, resulting in a disordered zone filled with debris. This belt is considered one of the most dangerous areas of the solar system for Earth. Many asteroids from this region could be nudged from their orbits and sent hurtling toward our planet. Some experts believe that the very asteroid that caused the extinction of the dinosaurs likely originated from this belt. If a giant planet had existed in that region to keep order, perhaps the age of dinosaurs wouldn't have ended so suddenly. Fortunately, this asteroid belt is a relatively small pocket of chaos. Thanks to the diligent cleaning efforts of the gas giants, the rest of the solar system remains remarkably orderly. In many ways, these 4 giant planets act as guardians of vast regions, maintaining stability across more than 4 billion kilometers of space. For life on Earth, their greatest contribution may not be what they contain or how they look, but the clean, stable environment they help maintain. They keep the solar system free of clutter, protecting Earth from frequent, life-threatening impacts. And their protective role doesn't stop there. These giants don't just clean up their own neighborhoods, they also act like celestial hunters. From time to time, they intercept comets that wander into the inner solar system, preventing them from ever reaching Earth. In July 1994, humanity witnessed one such event firsthand. For the first time, we observed Jupiter capturing and destroying a comet. The comet, later named Shoemaker-Levy 9, had actually been kidnapped by Jupiter's gravity over 100 years earlier. Once the comet's orbit was locked in, finally, in 1994, the comet could no longer resist Jupiter's immense gravitational pull and began to fall toward the giant planet. Before it collided, it crossed Jupiter's Roche limit, the point at which tidal forces exceed an object's internal gravity, and was torn apart into more than 20 fragments. These fragments formed a striking chain, spaced hundreds of kilometers apart, aligned like a procession on their final death march. These remnants of Comet Shoemaker-Levy 9, now dismembered, hurtled toward their ultimate fate, being consumed by Jupiter. Yet Jupiter didn't devour them all at once. Like a great beast that has captured helpless prey, it didn't swallow them in one swift gulp. Instead, it lingered, savoring the moment. The fragments continued to orbit the planet briefly, circling like condemned souls awaiting their end. Eventually, each fragment descended into Jupiter's atmosphere, one after another. It was an awe-inspiring moment in astronomical history. Though Shoemaker-Levy 9 had been torn into 21 pieces, the impact of each fragment upon Jupiter was still colossal. Experts calculated that each collision unleashed energy equivalent to the detonation of 100 million atomic bombs. The fragments struck Jupiter's surface at regular intervals, roughly one every 30 minutes. Given Jupiter's rapid rotation, its day lasts just about 9 hours. These impacts circled the planet, bombarding its surface in overlapping waves. Scientists estimate that the force of each of these impacts could have wiped out all life on Earth if they had struck here instead. In the solar system, a vast number of comets are constantly flying through space. It is estimated that over 100 million comets of various sizes pass through the inner solar system each year. Most go undetected by human eyes, yet each one poses a potential threat. Fortunately, many of these objects are intercepted or deflected by the gravitational fields of the 4 giant planets, preventing them from reaching Earth. What an immense security system this is, an invisible shield maintained across billions of kilometers and over billions of years. This planetary traffic control system is nothing short of extraordinary. We owe immense gratitude to these 4 gas giants, who silently guard the solar system and preserve its delicate order. Indeed, our solar system is a masterpiece of cosmic design. It contains an inner cradle of life, shielded by a vast outer ring of planetary guardians. Perhaps life is not the work of one planet alone, but the outcome of a collaborative system spanning multiple worlds. It may truly take a planetary team effort to protect, nurture, and sustain life. Mars, the 4th planet from the Sun, is one of Earth's closest neighbors, lying just 55 million kilometers away at its nearest approach. This distance is nearly identical to that between Earth and Venus. The existence of these 3 planets, Earth, Venus, and Mars, compels us to marvel at the remarkable architecture of our solar system. It may well be the most luxurious cradle of life in the universe, a near-flawless structure of engineering for the emergence of life. It seems the universe accounted for every possible failure, crafting three similar planets whose subtle differences minimize the risk of the life creation project going awry. Earth, Venus, and Mars, three planets whose physical dimensions are all suitable for supporting life, together form a dreamlike and opulent chain designed to make life possible. And then, against all odds, the miracle happened. Among these three planets, life emerged. The universe achieved its grand creative goal, but only on one of them. Only Earth stood out as the lone world to successfully harbor life. This reveals just how stingy the universe is with the gift of life. Even among three planets so similar and positioned in the so-called habitable zone near the Sun, only one was able to bring forth living organisms. This suggests that the final secret to life's origin might lie in hedging bets, having multiple similar planets in play and seeing which one succeeds. Yet, the blueprint of the universe is not one of mere repetition. Despite their similarities, these three planets each exhibit subtle but critically important differences. Venus and Earth are nearly identical in size, almost twin sisters in appearance. But their internal dynamics tell a very different story. Venus rotates extremely slowly, while Earth spins rapidly, and this difference may have determined their divergent destinies. Most experts believe that the stark contrast in their fates comes down to a single cosmic event, a collision. According to the latest research, about 4.5 billion years ago, Earth was struck by a Mars-sized body. This impact accelerated Earth's rotation and in turn triggered powerful internal currents within its molten core. These currents generated Earth's magnetic field. Moreover, the collision gave Earth an invaluable companion, the Moon, a byproduct of the impact. Venus, by contrast, experienced no such collision. As a result, it never acquired the momentum for rapid rotation. Without a dynamic core, Venus failed to generate a magnetic field, and without a moon, it lacked an additional stabilizing force. From a life science perspective, a planet's magnetic field is an essential shield, a kind of planetary dam protecting a vital reservoir. This is because sunlight carries a dangerous form of energy that can break apart water molecules. A magnetic field deflects this hazardous energy, safeguarding a planet's water supply and by extension its potential for life. In reality, water is an extremely scarce resource on planets. During their formation, planets emerged from blazing hot clouds of gas and dust, stellar nebulae, where any primitive water molecules would have been destroyed by intense heat and the young sun's fierce energy. As a result, newly formed planets were often born as dry, barren worlds. But to combat this natural drought, the solar system had a backup plan. In its early days, the solar system launched a vast delivery operation to redistribute its water reserves. At the outer edges of the solar system, there were countless comets with unstable orbits, frozen mixtures of ice and dust. These icy bodies acted as cosmic water carriers, transporting frozen celestial spring water to the inner planets. In that early era, the solar system resembled a grand celestial fireworks display. Comets, trailing long, vaporous tails of ice and steam, bustled across the skies, racing between planets to deliver their cargo. Yet once again, Venus missed its chance to retain water. Lacking a functioning internal dynamo, it failed to generate a magnetic field. Without this protective shield, the newly acquired water molecules were exposed to relentless solar radiation and once again lost to space. Earth, on the other hand, managed to retain its water. Thanks to its magnetic field, it formed a protective shield around the planet. This magnetic field acted like an invisible glass ceiling, allowing light to pass through while deflecting harmful solar energy. In doing so, Earth preserved the precious and limited supply of water it had received from the cosmos. Scientists believe that it was likely this very shield, Earth's magnetic field, that allowed the planet to become a cradle of life. Venus, without such a defense, lost its opportunity and passed life by. Mars presents yet another scenario. Though smaller and less Earth-like in size, it shares many dynamic similarities with our planet. In fact, Mars behaves like a miniature version of Earth. Like Earth, it spins rapidly on its axis, completing one rotation in 24 hours and 37 minutes, just slightly longer than Earth's day. Mars's axial tilt is also similar to Earth's, around 25 degrees compared to Earth's 23. This close match in rotational dynamics is striking. Scientists find this resemblance puzzling and suggest one plausible explanation. Mars, like Earth, may have experienced a massive collision in its early history. The impact was likely similar in both timing and angle, tilting the rotational axis and dramatically increasing the spin rate of the planet. However, unlike Earth, Mars didn't eject enough material to form a large moon. Most of the debris from the collision appears to have fallen back onto the Martian surface. The planet's two tiny, irregularly shaped moons, Phobos and Deimos, are believed by some to be remnants of that ancient impact. These two small satellites maintain odd shapes and lack spherical symmetry, consistent with the idea that they are merely leftover fragments from a violent collision. Back then, Mars may have been surrounded by many more such fragments, but over time, most of them likely rained back down onto the planet, leaving only these two survivors. Experts believe that Mars may serve as indirect evidence of the massive collision Earth experienced in its early history. That's because Earth's surface has changed drastically over billions of years, erasing most traces of its original state. In contrast, Mars has remained largely untouched, preserving its ancient topography. Without tectonic activity, Mars has kept the old face of a planet, one that reveals what planetary surfaces might have looked like billions of years ago. For Earth, Mars provides an invaluable reference for its own early appearance. Mars's terrain is remarkably structured. The northern hemisphere is dominated by low-lying plains, while the southern hemisphere is covered in rugged highlands. In essence, it appears that Mars's northern hemisphere is missing a significant portion of its crust. Most scientists attribute this massive hemispheric asymmetry to a violent external impact. It's likely that such a collision stripped away a huge section of the Martian crust in the north. According to planetary formation theories, a planet's crust should be evenly distributed across its surface. That means both the northern and southern hemispheres of Mars should originally have had complete crustal coverage. Only a powerful external force could have peeled part of it away. What's fascinating is that the loss of crust on Mars appears unnaturally precise, almost like a surgical excision. This pattern of damage doesn't quite align with what we'd expect from a straightforward, head-on collision. As a result, some scientists have proposed an alternative theory, that the damage to Mars might not have happened where it appears. In fact, they suggest that the actual point of impact was not the missing northern hemisphere, but the intact southern one. While this idea may sound counterintuitive, the cosmos is full of extraordinary possibilities. According to this theory, the colliding object struck the southern hemisphere of Mars with such intensity that it sent seismic shock waves rippling through the planet's interior. These energy waves traveled to the opposite side of the globe, shattering and ejecting a huge portion of the northern hemisphere's crust. Supporting this theory is a significant piece of geological evidence, a colossal impact crater in Mars's southern hemisphere. In contrast, there is no such crater in the north. And since Mars lacks tectonic activity, its surface retains a record of every major event in its geological history. This southern crater is known as the Hellas Basin. It measures an astonishing 2,000 kilometers in diameter and plunges 6,000 meters deep, making it the largest known impact crater on any planet in the solar system. Based on calculations, the force required to create such a crater would have been more than sufficient to fracture an entire planetary crust. Some experts believe this same collision may also explain Mars's rotation. Because the Hellas impact crater is slightly tilted, the angle of the impact could have not only dislodged the crust on the opposite side, but also accelerated the planet's spin, similar to how Earth's rotation was influenced by its own massive impact event. Experts have different views on the mechanics and dynamics of the impact Mars experienced. Each theory has its own logic and rationale. However, there is a general consensus. A massive collision did occur. Some researchers even believe that the enormous canyon along Mars's equator, Valles Marineris, was also a result of crustal tearing caused by this collision. This canyon stretches more than 4,000 kilometers, nearly the entire width of China. If placed on the moon, it would cover nearly half of its surface. Were there such a canyon on the moon, it would be clearly visible to the naked eye from Earth. Valles Marineris is not only astonishingly long, but also extremely deep, up to 7,000 meters. It far surpasses the depth of any canyon on Earth. What makes it even more striking is that this canyon was not formed in mountainous terrain. On Earth, canyons typically arise in uplifted regions where wind, erosion, and especially rainfall carve pathways between peaks. In short, Earth's canyons are mostly the product of water's erosive power. For a long time, scientists have been puzzled by the origins of Mars's Great Canyon, as it is located on flat terrain with no signs of surrounding mountain ranges. It seems as though the canyon simply collapsed downward into the plains. Its structure almost resembles an artificial trench. Observations suggest that water erosion is not responsible. Instead, the canyon appears to have been torn apart, pulled open by powerful geological forces. At one point, many experts classified Valles Marineris as a massive tectonic fault. But how such an immense fault line formed remained a mystery until now. Many scientists now believe that the driving force behind this colossal rift may indeed have been the ancient planetary impact. In that sense, the canyon itself is a form of physical evidence, a geological scar left by the collision. Such an impact would not only have destroyed part of Mars's crust directly, but also generated intense tensile stress in the surrounding crust, stretching and tearing it apart. When viewed from orbit, this rupture across Mars's surface does indeed resemble something violently pulled apart. Moreover, this tearing effect appears to extend sporadically into adjacent regions, creating a broader radiation zone of crustal fractures around the canyon. Studies suggest that Earth may have experienced similar collisions in its early history. But unlike Mars, Earth has active plate tectonics. The surface is constantly reshaped, like a planet undergoing continuous cosmetic surgery. Tectonic movement under the oceans and shifting continents have rearranged the planet's surface so thoroughly that the original scars have been transformed beyond recognition. Earth may never fully heal its wounds, but it has the ability to disguise them, remaking its surface again and again. Mars, however, tells a different story. Without tectonic activity, its crust has remained largely unchanged, preserving the face it wore when it first formed. This is why Mars might offer us a rare opportunity to roughly reconstruct what Earth may have looked like in the aftermath of its own ancient collision. Because Mars shares so many dynamic similarities with Earth, it serves as a natural replica, reproducing both the physical processes and the outcomes of such a planetary impact. This provides invaluable clues about the early surface structures that influenced the origin and evolution of life on Earth. In fact, this kind of collision is thought to have shaped the very basins that later became oceans. These depressions, which sit lower than the continental crust, are widely found on both Earth and Mars, but not on Venus. On Earth, these oceanic basins cover about 70% of the planet's surface, while on Mars they account for roughly 50%. Venus, on the other hand, has a crust that is almost entirely flat and uniform. This contrast strongly suggests that both Earth and Mars experienced major impacts, whereas Venus did not. For a long time, we've struggled to explain why Earth has oceans. It has always felt as though Earth's seas were dug out, but their distribution is so irregular that no coherent excavation pattern could be identified. Now, Mars's clearly missing crust offers a key to understanding this mystery. Perhaps Earth's ocean basins, the very depressions that hold the seas, were carved out by similar massive impacts. Over time, Earth's active tectonics may have obscured or altered the original impact sites, but the basins remained. We should be grateful for these giant hollows, these ocean bowls, because they are precisely what allow Earth's continents to rise above the water. Without these basins to collect water, Earth would be evenly flooded with no exposed land at all. And without dry land, evolution could never have progressed beyond a world of fish. Terrestrial life, including humans, may never have emerged. In this way, Mars offers a kind of geological diagnosis for Earth's early history, deepening our reverence for the universe's intricate engineering. Indeed, the universe seems to have solved numerous problems in a single, abrupt, and almost violently brutal moment. With one colossal collision, it not only triggered the formation of oceans, but also created the preconditions for life to evolve and flourish, reaching its apex in human civilization. But this raises another question. Why didn't the same miracle happen on Mars, which also underwent a similar collision? After all, the impact increased Mars's rotation, just as it did Earth's. Did Mars develop a magnetic field? Was there liquid water? Could it have supported life? According to multiple explorations and measurements, Mars did at one point have a magnetic field. However, this field was not only extremely weak, it was also fragmented, unable to form a cohesive shield around the planet. In effect, Mars had a leaky magnetic field. Such an incomplete shield could not protect the atmosphere or retain water molecules. Why was Mars's magnetic field so weak? Many experts point to its size. Mars has only 1/9 the mass of Earth, like a small boiler trying to match the output of a massive furnace. Though it rotates like Earth, its internal thermal energy is too low to generate the powerful dynamo effect needed to sustain a strong magnetic field. And without a magnetic field, Mars couldn't safely bask in sunlight. It couldn't shield its water from the sun's harsh radiation. And without protected water, life never had a chance to take root. Thus, despite having a surface structure seemingly perfect for the evolution of life, Mars lacked one critical ingredient: liquid water. Without water, nothing else matters. In this respect, Mars and Venus are like two ill-fated siblings. Both failed in their ability to support life due to fundamental limitations in their planetary design. Mars failed because it was too small. Its mass and internal energy were insufficient to sustain a strong magnetic field. Venus, on the other hand, was too passive. It barely rotates, and this lack of motion prevented the formation of a magnetic shield. Without that protection, neither planet could hold on to water. Still, while both Mars and Venus suffered from the same ultimate issue, drought, their circumstances are dramatically different. Venus, lacking water, could not absorb and recycle carbon dioxide. Over time, CO2 built up in its atmosphere, creating an incredibly dense and toxic blanket. The result was an intense greenhouse effect, turning Venus into a hot, dry, hellish world. Its average surface temperature hovers around 500 degrees Celsius, hot enough to melt metal. Mars, being farther from the sun, never developed such an extreme greenhouse effect. Its dryness is expressed through cold and desolation. The average surface temperature on Mars is around -50 degrees Celsius. The most extreme manifestation of Mars's aridity is its infamous dust storms. Mars is incredibly dry. Its surface resembles the harshest deserts and stony wastelands on Earth. But while Earth's deserts and Gobi regions cover about 1/10 of the planet's surface, Mars is entirely desert. As a result, its dust storms are far more powerful and widespread than anything seen on Earth. Even minor atmospheric disturbances on Mars can lift massive amounts of fine dust into the air, creating whirlwinds and local dust devils. These small-scale dust storms are a frequent occurrence in the Martian atmosphere. However, when atmospheric instability reaches a larger scale, Mars experiences global dust storms, truly planetary in scope. The largest of these can engulf the entire planet. On Earth, such a scenario is unimaginable. But on Mars, a global dust storm occurs at least once every Martian year, typically when the planet is near its perihelion, its closest point to the sun, during the Martian summer. These massive dust storms often originate in the Hellas Basin in the southern hemisphere. A small disturbance in this lowland region can gradually build into a massive storm front, expanding outward over days or weeks. Within a few weeks, the storm can cover the entire southern hemisphere. In more extreme cases, it spreads further, reaching into the north and eventually enveloping the entire planet. Such planet-wide dust storms can last 3 to 4 months, blanketing the Martian surface in a reddish haze. Today's Mars is, without a doubt, an extremely arid world, cold, dry, and dusty. Yet, just as scientists had largely concluded that Mars was an extremely arid and lifeless planet, a series of astonishing discoveries began to challenge that belief. Toward the end of the 20th century, NASA's Mars missions began capturing high-resolution images of the Martian surface, revealing areas that bore unmistakable signs of water flow. The findings were nothing short of stunning. These images displayed classic geological features typically shaped by the presence of water: flowing channels, erosion patterns, and valley systems that strongly resembled those formed by rivers on Earth. The terrain in many of these regions clearly suggested the action of liquid water in Mars's geological past. Did Mars once have water? One such image shows a Martian valley network, complete with branching tributaries and erosion channels. At first glance, these valleys look very much like river systems on Earth. However, closer inspection reveals important differences. Studies suggest that water on Mars may have flowed more like irrigation, rather than as part of a global river system. Unlike Earth's hydrological cycle, where rainwater collects and rivers flow toward oceans, Mars's water flow may have originated from concentrated underground sources. These subsurface reservoirs likely discharged water into localized channels, feeding the valleys from within the planet. This points to a possibility that Mars once had a very wet history, perhaps even an oceanic era, shaped by underground aquifers. And if water existed, the potential for life increases significantly. After all, water is the single most crucial ingredient for life as we know it. If Mars ever hosted liquid water, then the planet may have once nurtured life, perhaps microbial life from a long-lost Martian ocean. But so far, these conclusions are based only on visual analysis of Martian topography. To truly confirm whether water once flowed across Mars and whether it gave rise to life, we need more direct and definitive evidence, obtained through physical exploration and surface sampling. Among all the planets in the solar system, Mars remains the only one that shows surface features strongly indicative of flowing water. However, surface appearance alone is not enough. To scientifically validate the existence of past water, researchers must retrieve actual samples of Martian rock and soil and conduct comprehensive physical and chemical analyses. Achieving this requires landing rovers equipped to cover large areas, collect samples, and perform in-situ scientific studies. Among the most successful missions to date were NASA's twin rovers, Spirit and Opportunity. These rovers were equipped with robust mobility systems and 6-wheel rocker bogie suspension, capable of traversing diverse Martian landscapes over tens of kilometers. But they were more than just mobile scouts. They were fully functional laboratories on wheels. With advanced instrumentation, they could quickly collect, process, and analyze large volumes of geological, physical, and chemical data. Designed to maximize terrain exploration, these rovers were tasked with investigating the variety of Mars's surface features and geological diversity. To maximize scientific returns and eliminate any location-based anomalies, NASA deliberately chose 2 landing sites that were nearly the furthest apart from each other on Mars, each located at opposite ends of the Martian equator. This marked humanity's most geographically distant dual-point exploration ever conducted on another planet. The goal of this mission was to thoroughly investigate whether there was any conclusive evidence that water had once existed on Mars. In June 2003, NASA launched 2 intelligent surface rovers, Spirit on June 10th and Opportunity, MERB, on June 25, on a journey to the Red Planet. Spirit was the first to arrive. After a 6-month flight through space, it reached the Martian atmosphere. Given the sophisticated instruments on board, ensuring a safe landing was critical. To absorb the impact, NASA used large airbags to cushion the landing. Additionally, retro thrusters were deployed to reduce descent speed just before touchdown. After more than 7 months of travel, On January 4, 2004, Spirit landed near the Martian equator in a region known as Gusev Crater. This crater had long intrigued scientists, as it visually resembled an ancient riverbed or dried lake, showing signs that water may once have flowed through it. Once Spirit landed, a pre-programmed sequence initiated. The airbags were deflated and retracted, and the protective shell of the rover was opened. Soon after, Spirit rolled off the landing platform and began its exploration of the flat terrain. The immediate environment resembled a terrestrial Gobi Desert, with fine-grained sands scattered with rocks of various sizes. Spirit first approached a sizable rock later named Adirondack. Its surface was smooth and clearly exposed. Using instruments mounted on its robotic arm, Spirit analyzed the rock's composition through both surface abrasion and subsurface sampling. The analysis revealed that the rock was volcanic in origin, formed from ancient lava flows. However, to the disappointment of the science team, this ancient volcanic rock showed no signs of having been altered by water. It had endured in an extremely dry climate, untouched by moisture. This was discouraging, as scientists had theorized that Gusev Crater may have once held a shallow lake. If that were true, rocks from its basin should have shown chemical signs of water interaction, but they did not. Was there a fundamental error in interpreting Martian surface features? Were all those images of channels and river-like formations simply illusions? Could it be that the visual signs of water were nothing more than geological coincidences? Just as Spirit's early findings began to dampen hopes, its twin, Opportunity, touched down on January 24, 2004, on the other side of Mars in a region called Meridiani Planum, specifically within a small crater dubbed Eagle Crater. This area, too, appeared to be low-lying and bore features suggestive of ancient water activity. So what did Opportunity discover? The first thing Opportunity discovered was, once again, volcanic rock. However, within the images transmitted from this site, scientists noticed something astonishing. Scattered across the area were countless small, spherical pellets. These tiny spheres were almost perfectly round and were soon nicknamed blueberries, as they resembled the small fruits atop a Western-style muffin. Analysis using Opportunity's onboard instruments suggested that these formations were likely concretions, similar to oolitic stones found on Earth. Experts noted that such near-perfect spherical shapes only form under very specific conditions. One of the most plausible scenarios is a lakebed environment, where fine mineral particles slowly accumulate and roll on the lake bottom, gradually forming smooth, round shapes over time. These Martian blueberries were thus significant indicators that water had once existed here. But even more compelling was what Opportunity found within and around these concretions. Hematite. Spectral analysis revealed that most of the rocks in the region contained hematite, an iron oxide mineral that, on Earth, forms only in the presence of water. Hematite typically emerges through precipitation from groundwater, rainwater, or from hydrothermal systems. Its presence on Mars suggested that water had played a role in shaping the surface geology. Hematite holds special meaning even in human history. It was among the first pigments used by ancient humans. As a source of red pigment, its deep crimson color resembled blood, making it one of the most sacred and symbolic natural colors for early civilizations. Because surface hematite was relatively rare on Earth, it was reserved for significant rituals. Some of the earliest records of pigment use come from the Upper Cave people of Zhaokudian in China, who used hematite red in burial rites. Thus, Earth's hematite has long been tied to symbolism, scarcity, and reverence. But on Mars it seems to be abundant, so much so that the planet's entire red hue may be due to it. One could even say that Mars has been dyed red by hematite. This deep red tone of the planet is precisely why Western civilizations associated Mars with the god of war, the color of blood, violence, and battle. But does that mean there is less hematite on Earth than on Mars? Not necessarily. Earth likely has just as much hematite, if not more. But because Earth has an active, continuous water cycle, rain and surface water gradually carried the exposed iron particles underground over time. On Mars, however, water did exist, but only briefly. It was long enough to create hematite, but not long enough to wash it away. So while Earth's hematite lies hidden beneath the surface, Mars's hematite remains exposed. In this way, scientists believe the red color of Mars is itself evidence of a short-lived watery past. Mars was once wet enough to form hematite, but then quickly became dry, preserving the mineral on the surface as a geological memory of water's fleeting presence. And so, the hematite remained on the surface of Mars. In other words, Earth's hematite was driven underground by active water cycles, while Mars's hematite stayed above ground, left behind in plain view. Experts believe this planetary redness represents something profound. Mars is the result of a one-way evolutionary process, from a once wet planet to a permanently dry one. In the following days, Opportunity continued its investigation within Eagle Crater. It found not only more rocks showing clear signs of having been shaped by flowing water, but also made another major discovery through rock sampling: jarosite, a potassium iron sulfate mineral. Jarosite typically forms through the oxidation of pyrite, fool's gold, in acidic, watery environments. Because iron is such a reactive element in the presence of water, both hematite and jarosite are considered critical indicators of water activity. These two minerals, found in separate samples, serve as compelling evidence that Mars once had water. Opportunity was certainly living up to its name. In just its first landing site, it uncovered a wealth of signs pointing to Mars's wet past. Meanwhile, on the other side of the planet, Spirit was making progress as well. It had been journeying toward a mountainous region called the Columbia Hills. Along the way, it passed by Bonneville Crater and analyzed a large, fan-shaped rock named Mazatzel. This time, the outcome was different. Though this rock was also volcanic in origin, analysis showed traces of hematite in both the surface and internal structures, indicating it too had been affected by water. This was a key turning point. Now, two rovers, positioned more than 10,000 kilometers apart, had both found independent confirmation of past water activity. This ruled out the possibility that water-related findings were merely the result of isolated or regional phenomena. Opportunity continued to produce breakthroughs. It reached Endurance Crater, where it encountered layered rock formations bearing wave-like ripple marks, a clear sign of significant erosion by water. These patterns suggested not a brief wet episode, but a prolonged submersion in standing or moving water. Not to be outdone, Spirit lived up to its name. It boldly climbed the Columbia Hills, reaching an elevation of nearly 100 meters. There, it analyzed an exposed rock named Clovis. The results were stunning. Spirit detected high concentrations of sulfur, bromine, and chlorine. These elements are only incorporated into rock through chemical reactions involving water. The findings at Columbia Hills prompted a profound realization. Mars may not have just had shallow pools of water. It may have been deeply submerged. Even this elevated mountaintop had once been underwater. Taken together, the twin rovers' findings provide overwhelming evidence. Mars once had water, not fleeting moisture or passing rainfall, but stable, geologically significant bodies of water that shaped the landscape, altered rock chemistry, and may have once supported life. However, present-day Mars doesn't seem to offer the right conditions for liquid water. So why then did Mars once have water? In fact, Mars does have water today, it's just all in frozen form. Much of this frozen water is right in plain sight, at the polar ice caps. It was once believed that the Martian poles were composed solely of dry ice, solidified carbon dioxide. The temperatures at the poles can drop below 100 degrees Celsius, cold enough to freeze CO2 into a solid. Therefore, the brilliant white caps seen at the poles were long assumed to be frozen gas, not water. However, more recent investigations revealed a surprising truth. The bulk of Mars's polar caps is actually made of water ice, covered by a thin seasonal layer of dry ice. During the Martian summer, when the CO2 layer sublimates, it exposes the underlying water ice. And that water ice runs deep, thousands of meters thick, rivaling even the polar ice sheets on Earth. Radar data from Mars orbiters show that the northern polar ice cap is about 100 kilometers wide and up to 2 kilometers thick. For comparison, Earth's largest northern ice sheet, Greenland, spans about 2,400 kilometers but is only around 1.5 kilometers thick. In terms of depth, Mars's northern cap is actually thicker. The southern polar cap on Mars is even more massive, about 1,400 kilometers wide and up to 3.7 kilometers thick. Earth's Antarctic ice sheet, while broader, around 4,500 kilometers across, has a maximum thickness of approximately 2.5 kilometers. Again, not as thick as Mars's southern cap. Experts estimate that if all of Earth's polar ice were to melt, global sea levels would rise by more than 60 meters. While Mars's total ice volume is smaller due to its smaller planetary size, the potential consequences are still dramatic. If Mars's ice caps melted, they could easily flood the planet's lower-lying regions and form vast oceans. Of course, Mars's current climate cannot melt this water ice. Temperatures are too low, and atmospheric pressure is insufficient to support stable liquid water. But scientists believe that in the past, Mars may have been significantly warmer, and this warming likely wasn't due to sunlight alone, but rather to internal geothermal energy. One major contributor may have been volcanic activity. Although Mars has far fewer volcanoes than Earth, the ones it does have are colossal, dwarfing anything on our planet. These supervolcanoes are among the defining features of the Martian landscape. For example, Olympus Mons, the largest volcano on Mars and in the entire solar system, measures about 600 kilometers in diameter and rises 27 kilometers high, nearly 3 times the height of Mount Everest. It is the tallest mountain known on any planet. But why are volcanoes on the smaller Mars larger than those on the larger Earth? Does Mars have a more powerful core? Experts say no, the explanation lies elsewhere. On Earth, the crust is constantly moving due to active plate tectonics. On Earth, internal heat is released through the constant motion of tectonic plates. While the boundaries between these moving plates can generate localized pressure that leads to volcanic activity, such volcanoes are often short-lived. As the crust continues to shift, these volcanoes are quickly buried, deactivated, or destroyed. This is why volcanoes on Earth tend not to grow very large. Mars, by contrast, has no plate tectonics. Without crustal movement, magma has fewer opportunities to escape, and internal energy cannot be released regularly. As a result, when a volcano does form, energy builds up and erupts with concentrated force. Moreover, since the surface doesn't shift, Martian volcanoes can erupt from the same location for millions or even billions of years. That's how Mars came to host some of the largest volcanoes in the solar system. In fact, most of the dozen or so volcanoes we see on Mars today may have existed since the planet's early geological history. Through eons of repeated eruptions, they have grown into the supermassive forms we observe today. Experts believe that volcanic eruptions on Mars would have had dramatic effects on the planet's climate. Prolonged volcanic activity could have released enormous quantities of carbon dioxide and dust into the atmosphere. These materials would have triggered a powerful greenhouse effect, raising surface temperatures high enough to melt frozen water into liquid. Given the sheer scale of Mars's volcanoes, it's likely they erupted over very long periods. Scientists speculate that it was during one such era of intense, widespread volcanic activity that Mars experienced a warm climate phase, leading to the melting of ice sheets and possibly the formation of planet-wide oceans. Mars and Earth both rotate due to early collisions, and it is believed that in the aftermath of the impact, Mars's rotation was much faster than it is today. Calculations suggest that if Mars had spun twice as fast, its internal heat would have been sufficient to generate a planet-wide magnetic field. This magnetic field could have helped retain water molecules, enabling a full hydrological cycle and potentially fostering primitive life. While we don't know how long Mars's internal boiler remained active, the sheer size of Olympus Mons and other supervolcanoes indicates that this system may have sustained large quantities of liquid water over extended periods. Today, experts agree, Based on the growing body of data, there is no longer any scientific justification to deny that Mars once had liquid water. Then, on May 31, 2007, Spirit brought humanity yet another astonishing discovery. The rover had been driven so aggressively, like an off-road vehicle on rugged terrain, that its right front wheel eventually failed. The wheel became stuck and began dragging through the Martian soil, carving deep grooves into the ground. But this mechanical failure turned out to be a stroke of scientific luck. The grooves dug by the faulty wheel exposed subsurface Martian soil that had never been seen before. In this soil, scientists detected an unusually high concentration of silica, up to 90% purity. This kind of highly pure silica typically forms in ancient hydrothermal systems, hot, water-rich environments where life may have originated on Earth. This discovery drew a direct parallel to Earth's early biological history. Many scientists believe that the first forms of life on our planet emerged in similar hot, mineral-rich waters. The silica-rich soil on Mars, exposed purely by chance, may represent the most compelling link yet between ancient Martian water systems and the potential for life. Thus, the discovery of this high-purity silica-rich soil suggests that the site may have once supported a large population of microorganisms. In other words, while we have not yet directly observed life on Mars, we may have already found the cradle that could have nurtured it. This hypothesis is further supported by new findings. Recently, scientists were astonished to discover trace amounts of formaldehyde in the Martian atmosphere, at a concentration of about 1 part per 10 million. Experts believe this formaldehyde was likely produced through the oxidation of methane. Based on calculations, Mars would require at least 2.5 million tons of methane per year to account for the observed amount of formaldehyde. But such a vast quantity of methane is highly unlikely to be produced by non-biological processes. As a result, many experts now lean toward the idea that Mars may still host life today, if not complex organisms, then at least microbial life on a significant scale. On June 20, 2008, NASA made a major announcement. The Phoenix Mars lander, which had touched down at a high-latitude polar region, had dug into the soil and uncovered a shiny substance. Spectral analysis confirmed it was genuine frozen water, not just ice, but partially melted water ice, caught in a transitional state. This was the first direct sample of frozen water ever obtained by a robotic mission outside Earth. Scientists believe that in Mars's low temperatures, if enough salt is present, at levels about twice the concentration of Earth's oceans, the freezing point of water can be lowered significantly, even down to -28 degrees Celsius. Mars meets this condition. In fact, Mars is known to have a higher abundance of salt-bearing minerals than Earth, making the formation of sub-zero briny water not only possible, but likely. This revelation greatly excited researchers. It meant that liquid-like water may exist on Mars even today, not in open lakes, but as slushy gel-like brines locked in the soil. While not fully liquid, these briny films could still offer an environment capable of supporting life. Some scientists even speculate that Martian life might exist in these jelly-like pockets of subsurface water, protected by salt and temperature from total freezing. Others go further, suggesting that humanity should regard Mars with a new kind of respect, not merely as a scientific target, but as a world with potential biological dignity. If Mars truly has, or once had, life, our understanding of the universe and of ourselves would undergo a profound transformation. Humanity's exploration of Mars is now entering deeper and broader phases, pushing past the limits of earlier missions. We hope that in the not-too-distant future, even more monumental breakthroughs await us. For if Mars holds life, then the way life uses energy and resources in such a harsh environment may completely redefine our understanding of biological resilience and our relationship with nature. And if humankind can one day adapt Martian life through biotechnology, then the greatest extraterrestrial frontier in human civilization may not only be opened, but may offer us an entirely new perspective on life, survival, and the cosmos.